All right, good morning, everybody. Welcome to day 2. A little bit of a sparser crowd this morning. Good event last night. Maybe there are a few people still getting going a little bit earlier this morning. It was really a great day yesterday, and thanks everybody for your participation and contributions throughout the day. I've just got a few thoughts to start things off and share with you what some of the things that I saw yesterday. Just in case you didn't know, we've got roughly 165 people attending either virtual or in person, which is pretty amazing. The folks from the LF were able to get me a list of where people were from, both cities and countries, and so it's kind of cool to see where people are attending in person and virtually. So a really nice contingent from Czech Republic, our local host country, which is super interesting to see. Some speakers as well yesterday from the Czech Republic, which was great. Good representation from around the world. Lots of different countries represented, and really shows the diversity in the community, which is great to see. Then you go down to the cities, and there's lots of different cities also represented from those countries. And you know, Bangalore is a very largely represented country or city. Brno in the Czech Republic is also a city I'm familiar with, and as well as Prague, so that's great to see. And then just a lot of different people from different places, so it's been really nice to get to know you all a little bit in the breakout sessions as well. So a couple observations from yesterday. RTE flow came up several times, so that was interesting. Some new use cases, quantum safe computing, that was a really interesting talk as well. Some good presentations on different hardware approaches that people are bringing to the community as well. And AI even came up. What conference could you have in 2025 without AI showing up at least once? So that was interesting. And again, thanks everybody for joining the event last night. It was really great to see everybody. I was surprised at how full the restaurant was, and it was a really nice event. So thank you for joining. Again, today I think we've got a great lineup ahead for everybody today. Picked out an interesting one for me, just RISC-V processors. That's new technology that's going to be interesting to hear about. Also this afternoon, if you didn't notice, there's Birds of a Feather breakout sessions. Again, an opportunity to have some breakouts, deep dive into certain topics, and get together with people of a common interest area and go a little bit deeper and perhaps uncover new areas of collaboration for the community. And then we'll wrap up the conference. It'll have flown by. Two days seems like a long time, but yesterday flew by for me, and I expect the same today. So again, thanks everybody for coming, and it's been a great first day. Looking forward to today, and with that, I'll turn it over to the first speaker. There you go. So we've got QoS for DPDK-based cloud-native router from Juniper. So welcome, guys. Thank you. Looking forward to hearing about it.
Okay, good morning everyone. Hope all are doing fine. I am Kiran and I work for Juniper Networks. I am a software data path architect there, and been working on cloud native routing technologies. Along with me is my colleague Shailendra. He is the technical lead in the team. Together we'll be talking about some of the work which we've done on quality of service for a virtual cell site router. and the use case which we'll be mainly focusing today is the 5G front haul. With that, I'd like to start my talk by showing the evolution of the RAN from a legacy non-virtualized site to Open RAN architecture. The evolution is mainly about the RAN disaggregation. So the legacy non-virtualized site consisted of the BBU, or the baseband unit, and the RRH, or the remote radio head, co-located at a single physical location. The RRH processes the incoming and outgoing radio signals, and the BBUs did digital signal processing of the uplink and downlink data traffic. The BBUs were connected to the core via a backhaul transport network. Then some of the service providers evolved this topology and came up with what is called centralized RAN, or the CRAN. So here, they moved the BBUs into a central location. So the central location, like a data center, provided advantages like centralized cooling, and improved power efficiency, and easy management of the radio network. The BBUs connected to the RRH using front haul transport network. Note that these are just physical pooling of the servers, and there was no cloud involved here. Next came the virtualized RAN, or the VRAN. Here the functions of the BBU were virtualized and moved to the cloud. The cloud offered agility and scalability. But the interfaces of the BBUs and RRH were still proprietary, meaning the vendor interoperability was not possible. Then came the Open RAN, which made the interfaces open and standardized. The BBUs and RRH were further disaggregated into what we call RU, or the radio unit, the CU, or the centralized unit, and the DU, which is called the distributed unit. The RU and CU were called the front haul, and all these CU, DU, and RU came in the form of a pod or a virtual machine. Some of the functions like DU and RU could be orchestrated in a cloud-native manner using any orchestrator like Kubernetes. There was a new network element called the RISC, which was introduced to provide intelligence to the RAN network. So service providers used RISC to onboard third-party XApps or RApps into the network. So now, let's take the case of the front haul. In case of a physical DU, there needed to be a physical cell-site router to provide the transport network, but 5G had the option of virtualizing the DU, so there need not be any physical cell-site router here. So instead, there can be a virtual cell-site router, which can be run. It's a pure software router, which can be run on any x86-based Intel hardware, and also can be orchestrated in a cloud-native manner. In addition, the VCSR can also host the VDU function. So this was about the RAN disaggregation. So now this, we'll talk a little bit more about the virtual cell-site router, or VCSR. So this slide shows the capabilities and requirements of what a VCSR should have to cater to different use cases and solutions. Service providers use different technologies or deployment methodologies in 5G. They can be all the way from layer 2 to layer 3, or SR MPLS to SRv6, IPv4 to IPv6, BGP to ISIS. It varies all across. So the VCSR should cater to all these requirements. For the front haul, generally layer 2 or layer 3 is used, and for the mid haul and back haul, layer 3 is the choice. Segment routing is very popular here. For overlay services, people use VLANs using different layer 2 technologies like L2 VPN, VPLS, or VPWS. Now, if you talk about the latency requirements of 5G, so 5G offers very low latency compared to 4G. The latency, in fact, between RU and DU needs to be less than 150 microseconds. So it is very latency sensitive. So this is where we need to have a VCSR which should be able to produce very low latency, and care should be taken. Additional latency is not introduced here. So the end-to-end across all the components of the 5G needs to be less than 10 microseconds. 10 milliseconds. And there is also this control data and management traffic by the ORU and the DU. The VCSR should be able to assign appropriate priorities to these kind of traffic. Now, if you zoom into a little bit about the high-level block diagram of VCSR, this is how it looks like. As I was mentioning earlier, VCSR is a pure software router which can run on any x86 server and can be orchestrated in a cloud-native way using Kubernetes. And this is very much suited for 5G use cases because 5G is also cloud-native. At a high level, the VCSR has a control plane and a forwarding plane. The control plane houses protocols for routing like BGP, ISS, OSPF, and things like that. And the data plane or the forwarding plane is DPDK based, where the virtual router or vRouter runs. This provides very high throughputs, so that is the reason it is based out of DPDK. There is also this ODU, which comes in the form factor of a pod or container and is plumbed into the forwarding plane using a container networking interface, or what we call the CNI. The ODU exposes different interfaces towards the mid-haul, like data management and control. We call it the F1 interface. And the communication between ODU and the forwarding plane is generally, it can be, vhost user. For the front haul, for the RU side, ODU bypasses the forwarding plane and directly uses SRIOV to communicate with the RU through F2 interface. And for providing cloud-native functionality, there is a lot of Kubernetes machinery here. So there is a kubelet service, which helps in spinning the pod. And Multus is here used to provide different CNIs, like SRIOV CNI and CSR CNI. So this is the high-level block diagram. Now, a little bit more, we'll go to the QoS, and this is the architecture of QoS in 5G as defined in the spec. The 5G introduces this concept of QoS identifiers. So here, QoS is associated with individual flows. A flow is nothing but a data stream between the UE and the network. Each flow is associated with a QoS identifier, which identifies the parameters of the flow, like jitter and latency and throughput. 5G QoS has much more granularity and flexibility compared to 4G. Instead of having a single QoS value assigned to the entire radio bearer, 5G has a provision for having multiple flows with its own QoS requirements in the same radio bearer. So this helps the applications and services to receive tailored treatment based on their needs. Also, multiple QoS flows can be mapped to a single GTPU channel between the G node B and UPF, unlike the 4G. In terms of the mappings in the uplink direction, that is direction from UE, which is nothing but your mobile phones, UE to the network. The UE does the mapping of the QoS flows to the IP packets. And in the downlink direction, the UPF function running in the 5G core does this mapping. And the DU, which is running on G node B, translates these mappings to appropriate priorities, which is acted on by the VCSR. Now, there are two ways to implement QoS in VCSR. We have a way in hardware as well as the software. In the hardware, we can use NIC cards like E810 or X710 to implement QoS, and it is mainly suitable for bare metal servers, which has direct access to the hardware NICs. Here, the hardware, does all the QoS functionality like scheduling and queuing. So advantage of this method is that the hardware, because it's offloaded to the hardware, we get higher throughputs and performance. But the disadvantage is that it is not portable because it is dependent on the NIC. And it is mostly, NICs are fixed pipeline, so they are not tunable or customizable as per the needs. So the other way is to implement this QoS in software, and this is suited mainly for cloud environments which have VirtIO-based virtual NICs. Here, the queuing and scheduling of the QoS is done entirely in software. So advantage of this method is it is very much portable because it is hardware independent. And it can be tunable and customizable if there is any optimizations that needs to be done because it's just software. But the disadvantage is that it has a lower throughput compared to hardware because software is the one which does the processing, and sometimes entire CPU cores needs to be assigned for this functionality. So in the rest of the presentation, we'll mainly focus on the software-based QoS and how DPDK is used to implement this use case. And I'll request my colleague Shailendra to talk you through those slides. Thank you.
Good morning, everyone. So with high-level architecture, we have a clarity now on how 5G high-level architecture works. So we will stick to the DPDK specific things. So this is a cost pipeline. It is well known. We have a classification, policing, and marking at the ingress level. So classification is basically association of incoming traffic with the specific traffic class or forwarding class. This classification is very important because if you cannot classify the incoming traffic into voice, video, different categories, you cannot act on them in the further cost blocks like shaping, scheduling. Categorization is like the primary start for the cost pipeline. For the policer, now, once the classification is done, like I mentioned, it gives you a result as a forwarding class. And the classification is done on the DSCP bits. For V4, we have toss byte, and first 6 bits of the toss byte are the DSCP bits. Similarly, for V6, we use TC byte. They are called differential services. And we use code point to program most of the classification rules. We'll be referring to them as DSCP bits in the upcoming slides. So policer takes input from the classifier. So classifier basically has given the forwarding class and the loss priority. Loss priority is mapped to the color. Loss priority high means a probability of dropping the packet in the QoS is higher. Loss priority, we have 4, high, low, and medium high. These are mapped to actually 3 colors in the backend. So high means red, medium together with the yellow on the color, and the low means green. Once we go to the polyser just works on the colors. Now polyser, we have 2 types of polyser in DPDK implementation itself, SRTCM and TRTCM, single rate tricolor meter and 2-rate tricolor meter. For both, they work in color aware and color blind mode. Color blind mode means whatever classification has marked the color or the loss priority, the polyser will not look at it, it will not honor, it will just act on the configured rates and provide you the output color without considering the input color. In color aware mode, it does take the input from the classifier color and then work on it accordingly. So for example, the input color is green, so output color would only be yellow or red. If the input color is yellow, the color would only be yellow or red. If it's red, then it stays red. So that's for the polyser. Now, once we have the forwarding class and DSCP bits are associated with the forwarding class, we call that packets are marked in the pipeline. So next block in the pipeline is at the egress, that's a rewrite. Now, once the packets are marked by the classifier, you have some certain requirement or certain use cases where you want to override the values depending on where you are forwarding. In router, you have multiple interfaces. Packets are coming in from multiple input interfaces going out. And input priority or input classification is done for overall traffic with certain rules. And you want to send the packet out, but you want to change the priority, you can do that using a rewrite. So it will override the DSCP bits for the particular forwarding class. The next module is the shaper, scheduler. Scheduler has submodules like shaper and the congestion management. Scheduler is implemented in our pipeline as a separate block. So what scheduler does is we have a forwarding class, or once we have an output from the classifier and the polyser, which is a color or the loss priority. Scheduler input is mapped with that forwarding class, so forwarding class to the scheduling. In this particular example use case, we will be showcasing only the strict priority scheduling. There are multiple different scheduling algorithms, but for simplicity, for use case, we'll be talking about strict priority scheduling specifically. So forwarding classes will map to the queues in the scheduler, and that's will be the input to the scheduler. Now output from the scheduler, as part of scheduler definition, you can configure rate, congestion management parameters for different drop profile using different drop algorithm. In DPDK, we have WRED and the PI support for dropping the packets. We will use, for our use case, we will just showcase the WRED in our configuration in the backend to drop the packet. So this will help us achieve, because we are doing the strict priority scheduling, we have a chance where high priority queues can starve the low priority queues because you have traffic coming in from multiple interfaces and your bandwidth is limited towards the egress. So in 5G use case specifically, we typically apply the QoS or the scheduler towards the mid-haul interfaces. So multiple RU interfaces are aggregating the traffic, and traffic is going towards the core on the mid-haul interfaces, and that's where we apply the scheduling. So you would have an option to choose disable or enable scheduling per interface basis. This is the existing DPDK pipeline, which is supported from a really long time in DPDK. We have packet parser, packets coming in and the RX. We apply the classify polyser, and then the packets get load balanced to the different worker cores, and then eventually combined at the later module at the scheduler, and then TX out. This pipeline we are showcasing for VCSR because I talked about there are requirements to do selectively on some interfaces scheduling. It is processing intensive. So what this diagram is showcasing is also the use case where the pods are connected to the router. You have physical interfaces. For example, in this particular diagram, we have a fabric WIF1 showcased here, which could be VF or a PF. In certain use cases, because ODU exists and some customer says we don't want to touch our code, we don't want to modify our application, it works on SRIOV, just use the SRIOV. So we use the VF the interfaces towards which are in the DPDK will just act as a gateway. All traffic will be forwarded to the switch to those interfaces. But there are scenarios where the pod can act as has a capability to do the what IO interfaces or MEMIF interfaces. So our CNI helps stitch those interfaces into the VCSR, and that can be the incoming interface for the router. So we apply, once we receive the packets at the forwarding core, we have received the packets, now we can apply the classifier, polisher or marking. These are our ingress blocks. Rewrite is shown on this, but it is typically after the routing decision is made and you have decided which egress interface you want to send the packet out on. Now, in this diagram, let's say your egress interface is interface 3, wave 3, which is a fabric interface, and on that interface you have not configured the scheduling, so it will act as a run to completion mode and packet will go out. Performance for this would be slightly better. For scheduler LCORs, if the egress interface that was selected from the routing decision has the scheduling enabled on it, it's a mid-haul interface and the packets want to be going towards the core. We are dedicating a separate LCOR for this functionality, and this would do the scheduling, shaping, congestion management, all the blocks that we'll be talking in detail about, and then the packet will go out on a TX. So it's a hybrid of a run to completion or pipeline model, which fits the VCSR use case need. So what we will be showcasing now is how we are really leveraging the DPDK for different blocks, like what APIs we used from the DPDK for doing the classification, for polisher, for scheduling functions, and how it really looks like from the router point of view. You're doing a configuration in the router. So for the configuration context, we have taken a simple JSON format to represent any router can do this. Let me jump further into the classifiers. Now, classifiers are crucial, like I initially talked about also, because they provide the foundation block for managing and prioritizing the traffic. Without this prioritization, further blocks cannot act on them. We talked about the DSCP bits are used. So you notice here in this is, there are two types of classifier, a single field classifier and a multi-field classifier. In single field classifier, we have a loss priority and the code point mapping. So in the packet, the code point are the first 6 bits, like the DSCP bits. It's also referred to as a code point. So we match the packet, we assign the loss priority based on the configuration from the router, and this defines the forwarding class. Now we have a classification of a packet. We know it's a voice, video, based on the configuration, a user can select this. These are named as CLA1, you can name it as anything. That's the forwarding class definition for you. So in single field classifier, you expect the packets are already marked, they are coming in with the DSCP bit in a proper prioritization. Now there are cases where that is not the case. So what you want to do is you want to use a multi-field classifier, which can match packet on any 5-tuple rule, IP, ranges, masks, different combinations, and create a classifier for you. Eventually the output is the same, the loss priority and the code point combination is created, and we have a defined forwarding class now. Now loss priority, like I mentioned earlier, is also associated with the color. So the next module in the pipeline, which is a polisher, takes input as a color. This showcases the DPDK APIs. For a single field classifier, it's a straightforward match on the DSCP bit. But for the multi-field classifier, we use the ACLs. So it's well known, I don't go really into the details, so we define an ACL. Now, for VCSR, it's a dynamic creation, so you can add and delete the ACL rules on the fly. That, like Kiran showcased, we are doing it over the gRPC as an example. ACL classify is for basically the packet matching. I'm not showcasing the deletion and other things for simplicity to keep the slide simple. This diagram explains the data plane view. Now, once you have programmed the rules down into the data plane, it's a table that showcases the code points and the loss priority and forwarding class mapping. So it basically also tells you which packet is having a what forwarding class association. In the packet, if, for example, the code point is programmed as 42, in the packet it will be hex A8 because first 6 bits are used. Next block is polisher. Classifier gave us an output of loss priority, and the data plane now has the programmed values and the mapping from the forwarding and the understanding of the forwarding class. Polisher, we have 2 types of polisher, SRTCM and TRTCM. Both work in colorblind and color aware modes. And Polisher uses a token bucket algorithm in the backend to shape the traffic, rate limit the traffic. So we have, if you notice, we have two definitions. We are showcasing both the SRTCM and TRTCM definitions. There is a slight differentiation in the parameters, like tricolor meter TRTCM uses two rates, peak rate and the burst rate. And eventually, based on the rate exceed or the configuration values, we decide what color of the packet is. And this is a well-defined standard. We have an RFC for this, and RFC recommends what kind of values you should use for the traffic classification. Applying this polisher in the packet path. Now, you have the polisher definition. How do you really stitch it in the packet path, right? So for that, we again use ACL. ACL can match based on the forwarding class, and then associate that polisher with that forwarding class. So now we have two blocks stitched. We have the classifier, and the packet can be polished together. Output of the polisher is color. Now, based on the color, you can choose. If it's red, you want to drop the packets, you can drop the packets, or you want to take some other action, you can take that action. These are the APIs from the DPDK that we use. I am not showcasing here the RFC 4115, which is also implemented in the DPDK, and you have the APIs available. So we are basically defining a profile here in the configuration. You have a profile application to the meter flow, and then based on the color aware or color blind mode, you can call the API, and it will give you an output of the color of the packet. And you can choose to drop or forward accordingly. This is the DPDK view, a data plane view of the programmed values. So we have an index. We have the name for the polisher, and we know it's associated with what last priority, what color, what are the values configured. It's basically, so the last field is like PBS or EBS. In the single field classifier, you use the PBS. We are using the common field to display. Rewrite. Rewrite is applied on the egress after the routing decision, like I mentioned, on a router. So this can override the values of the classification that is done by the classifier or polisher. So this helps in deciding what you want to send to the next router. So there is, again, a classification or a standard for this, which defines per hop behavior, and accordingly you can choose the values. This showcases the DPDK view from the data plane, what it looks like. So you have an input, two inputs, forwarding class and the lost priority, and the output is rewritten DSCP bits. Next module is scheduler in the pipeline. So DPDK supports hierarchical scheduler. The representation are, you have a port on the top. Port represents an interface. You have a subports, which represents a group of users. You have a pipe, which is basically used for a user or a specific subscriber. You have traffic classes, which represent different type of traffic. It's same as forwarding class. And then you have the queues on which you will be taking a queuing decisions, or based on, you can do the shaping and congestion management on those queues. So what we have done, like I mentioned, we will be using an example of strict priority scheduling here. In most of the VCSR use cases, it's 8-queue strict priority scheduling that most of the customers use. That's the most common use case. So what we are showcasing is how we customized or tweaked the existing hierarchical scheduler in DPDK for the strict priority 8-queue use case. So what we have done is we have one support, one port against one support, we have one pipe, and then we have 8 queues. So what we did is we just tweaked the profile settings, and this becomes like a 8 queue. There's no user awareness, no subscriber awareness. It's just 8 queues, and based on these 8 queues, you can, based on the lost priority or the classification of the packet, you can do the scheduling in the scheduler. These are the scheduler configurations. We have this is just specifying, like, you can create a scheduling for voice with the different values. You can have a priority. Priority is basically, in this particular use case, was mapped to the queue specifically. So 8 queue, we have 8 priorities that can be mapped 1:1. You can configure the transmission rate, which is a criteria to shape the traffic. You have a drop profile, which helps in congestion management. Now, like I mentioned earlier in the strict priority scheduling, higher priority queues can starve the low priority queues. So that's where this transmission rate or shaping rate comes into the picture. You can configure the specific rate on the higher priority queue. It basically then you don't starve the low priority queue, and traffic can be tuned accordingly. Drop profile, again, we have multiple different algorithms for drop profile. For simplicity, we are just showcasing a red. You have min threshold, max threshold, and mark probability. If it's applied on a queue size, if queue size is below the min threshold, everything goes through. If it is higher than the max, everything is dropped. If it is between min and max, we drop the packet based on the drop probability. Denominator, if it is 10, if 1 is to 10 of the packet are dropped. These are the APIs, existing APIs from the DPDK that we are using for this function. We have a scheduler port support and a pipe configurations. You configure those, and then you apply the profile. And then based on once the profiles are applied, you have the data path tweaked for the purpose. And then what we do is, how do you pass now? How do you stitch the scheduler to the previous blocks, right? So you pass the color as an input. So we mark the packet in the RTM buff. So there's an API scheduler port packet write, which overwrites the value. And internally, the scheduler code uses the color and the forwarding class as required. So then we enqueue the port, dequeue the port, and after the dequeue, the packet can be sent out on the physical NIC, TX. So this shows data plane mapping internally on how the priority queues are mapped to the forwarding class. What I did not show in the previous diagram was the map configuration. So you can associate a forwarding class to a scheduler, and scheduler defines the priority. For example, strict priority in a previous diagram, if you notice, was part of the configuration of scheduler definition. Sorry. So now all the scheduler definitions are mapped with forwarding classes. You can choose each forwarding class at what shaping rate you want to configure. You can choose to apply or not apply drop profile. Drop profiles are again applied per color basis. This is the drop profile definition. I talked about this earlier on what criteria we drop the packet, and the queue size is really important. This shows the packet path at runtime. So for this example, we had configured the scheduler port configuration to be at a 5 gig, and the incoming traffic was higher. So you notice here, the queue length is like free for the higher priority queues. So the packets are being pulled faster for those, and the lower priority queues are being starved. The queues are always full, packets are always dropping. So it's the starvation case I was talking about. Now once you configure the shaping rate, you notice everything is equal. Still the port is still oversubscribed, so we're still seeing drops. Average queue length on the higher priority, because each queue is oversubscribed. So that's why you're seeing those numbers. But low priority queues are not starved anymore. For future work now, we identified some limitations in the DPDK ACL library. For like our use cases, we see there are a lot of cases like people want to say match on port 100, port 500, port 600. It does not fit the mask capability that the ACL library supports, so we end up adding 3 rules. So we can implement the list maybe, and that helps us. We'll explore all this work and see if the routing use cases can extend these capabilities. So for the drop profile also, we have a very limited set. Even in fact in the red, we just do the min max probability based drop. We have seen that we can do on a multiple level the drops. You can create an interpolate graph, take multiple min, multiple max, and create a step graph, and that helps in the congestion management in a much better way. So we will see if we can extend the library for that. So runtime updates for router needs everything at runtime, right? So you can't have an init configuration and stick to it. So I think runtime updates APIs are missing. So we'll work with the community to extend it to update, to bring in the runtime updates. JCNR is an example of what I just showcased as a VCSR. We have everything implemented in the JCR and much more, and now we'll see if we can work with the community to have the better use case and bring those in. These are some references for classification, metering, and the cost framework that we talked about. So thank you. We can take questions if anyone has.
Thank you. A nice presentation. Thank you. The first question, this is the scheduling for the traffic. So as far as I know, in 5G core, there's a component, PCRF or PCF, which does the traffic shaping for end users. And how does it map to your approach? Because if I remember, if I understand correctly, the CSR is the RAN part. So it's not a 5G packet core. It's on the edge of the network. So how do you implement the interaction with PCF? And the second question, you use Virtio user for interaction over F1 interface. So is it okay with you in terms of performance? Because if I remember correctly, it doesn't have zero copy option. So is it okay with you guys?
Yeah, so especially let me start with the Virtio first. So for the Virtio, what we see is the ODU, what we are doing is we are deploying at the RAN side, right? So you have multiple radio networks, multiple RU interface. So you have 8 different RU interface coming in, consuming the traffic. And then they are switching it to the data plane or the router, right, VCSR. So what happens is the radio itself has a limited capacity. So on a particular cell site, so far all our use cases, we have not seen the traffic going towards the mid-haul exceeding 25 gig, right? That too at an IMIX traffic rate, not at a 64 byte packet size, right? And you have multiple such units. So we are talking about deploying like 20,000 units. So it's at a very small scale that is deployed at each. So this particular use case is talking about that. Being said that, we have the MEMF capability. You can use MEMF. You can use VF directly, SRIOV VF, where you stretch the traffic via the VF and that hits the router interface. And we act as a gateway for those pods. So you can do that. So you have multiple options. We have a transit router use cases. If you want to just work on the physical link, you can work on the physical link. So those options are available. Now, for the first question, because we are at the RU interfaces, there are multiple RU interfaces that are aggregating the traffic. So for this particular use case, you want to apply the scheduling or shaping towards the traffic that is going towards the mid-haul. What you're talking about, the PCRF use case, are towards the core.
So just adding, right? So in this slide, we are at the G node B level. What you are talking about is the 5G core. Right? So the use case is a little different for us. So there is no PCF here. This is a DU functionality.
No, I understand. I mean, what's the, do you have an experience implementing integration in PCRS in terms of using that API for DPDK to implement the traffic scheduling in the 5G core?
So far, from the customer ask, it is mainly on the access side. Core side we have, but then we really haven't got any requirements for the PCF side of things. We have a VPC use case there, wherein we have a tunnel established from the G node B mid-haul, basically CU to the 5G core, right, and not really the QoS part of it. And you have that backup slide for the.
So do you see any limitations on changing things at dynamic, like the scheduling hierarchy, right? You cannot change at runtime, right? And RTACL rules you cannot insert at runtime, right? So how do you manage that?
We are able to manage that. We are not seeing, so for ACL rules, we curate a context and we switch the context together. And the rules stay within the context. So that way the ACLs are simple and it works. For the rate configuration, shaping rate works perfectly fine with the dynamic updates. The APIs are not there in the DPDK right now, but the shaping rate update, we don't see any issues. Especially in the diagram in the architecture, if you noticed, we are not doing it in a multi-threaded way. It's a single L core that handles the single NIC. So it really becomes seamless. So we dedicate the scheduler L core based on the NIC. One scheduler can have multiple NICs, but one NIC cannot be spread across the multiple scheduler L cores. Because the use case was very limited here, 25G was the max case, so this works very well.
Only the hierarchy cannot be changed. But
hierarchy we are not changing because we have, like I mentioned, for a strict priority use case, we have fixed the 8 queues and we never associate like the port or subports with the user or a subscriber. So it's based on the traffic class. So 8 queues are fixed, so scheduler hierarchy is fixed. we are not changing the hierarchy in this particular use case.
Okay. So ACL case, it's like a ping pong buffer, like you keep changing. Okay.
Correct.
That's a good idea. Okay, thanks.
So we have done the changes for the dynamic updates, like what Shailendra was saying. Maybe we'll need to upstream those changes. Right now it's in a fork.
Yeah, that would be great because this dynamic aspect is missing in DPDK.
Yeah.
So this, if we can
Correct.
upstream, it will be good for community.
Sure, that's the reason we highlighted it here. Good.
Hello? So is it using, is this the QoS DPDK QoS implementation?
It's the hierarchical scheduler implementation.
Okay, in DPDK,
Correct. Yes,
it's
correct.
QoS. In my experience, it has limitations more, it doesn't scale beyond 2K flows. Do you have experienced any limitations, and do you plan to improve that scaling? Because without scaling, with scaling, if you can improve the scaling, it is very useful feature. But I think the implementation was done a long time ago by, I don't know who was the original developer, but after that nobody has touched it. But I think there's a lot of room to improve that scheduler for large scaling.
True.
Then it becomes very attractive.
Yeah, so in this particular use case, we are not really tying it to the flows. It's really tied to the packet match, and you just go to the queue. Queues are fixed, 8 in number, so we are not having a big hierarchy, so that way the scale numbers are okay, and we are able to do actually 25 gig with iMix traffic.
I mean, okay, so you're basically matching packets, not flows, and then...
and this packet goes to the queue, and pretty much queues are 8 queues, fixed in number. We are never changing the hierarchy of the scheduler.
Okay.
So
Okay. I mean,
25G, at least for VCSR use case, you never need more than 25G as per our experience so far.
Yeah.
And that too not with 64 byte packet size. We're talking about like iMix traffic. So the PPS is not really very high. So in that context.
So basically, I'm just trying to understand, you said you're doing packet based, right? That basically multiple flows goes to the same queue, right? Correct. In this case, how do you ensure that, consistency in the, end to end for a certain, because everything is flow based, right?
Sure.
People are sending,
Sure.
HTTP, watching movies and stuff
Sure.
like that.
Sure.
So anyway, all right, thank you.
Yeah, my question is pretty much the same context. Right now we are using the 25 gig, but in the future, right, it will be like 100 gig and even more for PCI Gen 5 and Gen 6. So given that current latest all the vendor, right, CPU vendor, like including AMD, we offering the high core count CPU, right? So given that, because right now we have more CPU to utilize, so you talked about some scaling kind of, the strategy while you're doing the QoS for CSR. So what is your approach, and think that is how we can utilize those many cores throughout your pipeline model?
So if I get the question correctly, you're asking about how do you scale this given that CPUs are more now, and then tomorrow if you want to support higher bandwidths, right, throughputs,
Correct.
How can you do that? So one type of scale which we've implemented here is we are tying one scheduler L core to one NIC. Okay, so if you have multiple NICs, let's say 4 or 5 NICs, right? This might not be the same VCSR use case, but for some other use case, because we have more CPUs, we can associate each CPU to one NIC, right? And the entire CPU is dedicated for the scheduling functionality. So even if that NIC is, let's say, 100 gig, it can do it because there is no packet processing done here. It is just queuing and scheduling, because packet processing which is more intensive, CPU intensive, right? The route lookup and next hop lookup, everything, that is actually done in the forwarding cores. So this is one way, scalable way of extending this architecture. Okay.
Slightly different question. Working? Okay, yeah. Slightly different question. So you said this whole orchestration is happening as a pod. Is there a reason for using pod? I mean, is it?
Yeah, so for cloud native use cases, most of the customers have adopted Kubernetes, and they are using complete orchestration using Kubernetes. We have worked with vendors like Wind River Cloud Platform. We have basically many platforms, right? So it's like a generic, we are agnostic to the platform, but major cloud native use cases are coming with Kubernetes.
Yeah, so the purpose is just the containerization or also being, like this whole thing is being published as a service?
The reason is this workload, right? This workloads are containerized now. So 5G has, has the architecture of cloud native itself. So the ODU is a pod now or container.
Okay.
Right, so the router should also be, in the same form, cloud native router.
Basically, the vendors, whoever we work with, they are looking for a unified orchestration platform. They don't want it to be a VM and then they bring in pod. How do you stitch it to VM? Right.
Right. But my question was like, are we publishing this as a service, a Kubernetes service where you load balance also? Those features are.
So right now it is present as an infrastructure layer.
Okay.
But for this particular use case, so there are other use cases where you're acting as a transit router, let's say. In that case, sure. In that case, it works.
Okay.
This is maybe a kind of a generic but very specific question. There's initiatives going around focusing on latency. Specifically RFCs regarding L4S, low latency, low loss, scalable throughput, where you typically have dual queues. So all applications using non-L4S aware protocols use classical queuing, and applications that are L4S aware use low latency queuing. And this kind of requires dual queuing or something else. What are your plans for L4S support?
It's in the pipeline. Right now, we have not done much work on that area. We are just using the cost scheduler from the DPDK for now.
Okay, so no plans to implement L4S as scheduling in...
Not immediately.
No, okay, thanks.
All right, it looks like we're at the end of questions from the first presenter. Thanks, guys.
Thank you.
Next, we've got a virtual presenter. So we've got Christian from Intel coming to talk to us about how to make your data center switch smarter. So we'll just give the guys a couple of minutes to get set up, and then we'll dive in.
Hey folks, good morning. the smart switch use case. So essentially, how to use DPDK to make a data center smart switch, to make a data center switch a bit smarter. We'll give you an overview of this use case called Data Center Smart Switch, and we'll take a quick look at the pipeline, the data plane pipeline for this use case. And then we'll gonna look at how we implement this complex pipeline on the Intel IPUs. More specifically, we have an Intel IPU adapter E2100 that we used for this exercise. And then we also take a quick look at the performance of this pipeline running on this IPU device. IPU stands for Infrastructure Processor Unit. Essentially, it's a smart switch. It's a smart NIC. Other names in the industry are also DPU, Data Plane Unit. We use the IPU name for this part. So taking a quick look at this use case, what exactly is the smart switch use case in a data center? As we all know, a data center is mainly made of switches and servers. And in order to make the data center smarter, we need to have smarter switches, we need to have smarter servers. Now, on the data plane side, we could use servers to do some part of the data plane, namely the more complex processing that the switch usually is not able to do. Or we could also focus on the switch. Obviously, we need to focus on both sides of the problem. Now, for this discussion, we look at how to make the switch smarter. And obviously that could result in some cost reduction if we don't use the servers which are usually expensive. If we don't use them to do the data plane processing, if we could do that on the switch, then that would obviously lower the pressure on the servers, and we can use the servers to run VMs and other workloads that are not basically fundamental data plane packet crunching, right? So usually a switch is a device that processes a lot of packets very fast, but the processing is simple. And that is also a consequence of the fact that the switch usually, although it has like a significant amount of internal memory, sometimes you can also add external DDR to the switch, but usually the tables are reasonably small versus what you could do on a server or on a smart switch, where you could add more DDR memory and have bigger table, more tables. You have CPU instructions. Usually the switches are not programmable. Some of them are, but they are exceptions. And it's kind of difficult to program at a high level. You could use the P4 language if your hardware supports it, but still you tend to get into limitations related to what instructions and what actions, what programs can you actually put on a switch. So then all those processing workloads that require more complex processing would actually go on a smart NIC. So then a smart switch essentially is a switch that does things very fast and very simple, plus a bunch of smart NICs, right? We could equip some of the external I/O ports of the switch with some smart NICs, and then those smart NICs would do the complex processing that is involved sometimes in or pretty much every time in a complex data plane pipeline. Although it's not going to work at the same speed as a switch, but it does the job, because not all the traffic needs to go through this complex processing path. It's usually some of just a subset of the input traffic, and most of the traffic usually goes through the switch without going through these smart NIC devices. Now, there is this concept is like very live and kicking in the industry. Is promoted by some people. One of the great promoters of it is Microsoft. They have this smart switch use case, and they also document it publicly in this project called Sonic Dash. Sonic is a network OS. A Dash is basically an extension to this to the Sonic NOS. And that essentially allows for some of these pipelines to be created, provides APIs, and provides like the specifications for the pipelines that need to be there on the smart NICs together with the switch in order to make the switch smarter. So in case you are not aware about this project, I fully encourage people to go on GitHub on the SonicNet Dash project and take a look at the documentation folder. It's a very complex folder with a lot of information about things that could be useful in order to make a switch a bit smarter. So essentially, the processing, the data plane, instead of going on the servers, it's not going to the switch either, but it's going to the smart NICs that are part of the switch, and logically everything is part of the switch. So taking a look on the pipeline here of the data plane pipeline of this project that we call Sonic Dash. Which is a more specific instantiation of the smart switch use case. This is not the easiest pipeline to explain. I'll try to do my best and do it quickly as well. So one of the there are multiple use cases part of the Sonic Dash project. One of them is called VNet to VNet, and that's what we are going to focus on. It's essentially a virtual switch. And its purpose is to connect virtual machines that are geographically apart, right? They could be on different continents, but still we can create this abstraction that everything is part of a big, nice global data center, right? Now, let's say you have two VMs that are very far apart from each other. Each of them has to be connected to a smart switch, right? So think about two endpoints, two VMs, and on each side there is a smart switch. Now we can locate ourselves on one of these switches and say this is the local switch and this is the local VM, and then we have a remote VM that is some other part of the world. And that's also located. That's also connected to another switch, which is the remote switch, right? So it's about the two VMs talking to each other through these two switches, right? Obviously, in the middle there could be could be the whole internet with many other nodes and switches, right? So the main blocks here are essentially the flow lookup with connection tracking. So basically one VM initiates a connection, it sends packets to another VM, that VM needs to reply back with the packets. So yeah, we can focus on the TCP use case, which is more connection oriented as a protocol, right? Or we can look at a UDP connection. I think it's easier to explain it for a TCP connection. But before that, basically just to go quickly through the main blocks, on connection tracking side, we try to discover new connections, right? And we want to basically register them in our database of flows or connections. At some point, we also need to forget about those connections. For example, when we have a timeout, we don't get any packets for a long time, for a reasonable amount of time on that connection. We need to delete it from our table. Or in the case of TCP, there is also a graceful procedure to finalize a connection through the FIN sequence, right? So we need to detect that. So we try to monitor the state of the connection. We try to discover new connections, register them, but also we need to monitor the lifetime of the connection, see what happens with that connection. And we are like the man in the middle. We are not going to run the TCP state machine. It's the endpoint VMs that are going to run the TCP state machine. But we are a man in the middle. We are a switch. And we need to monitor the connection, right? Because if we don't monitor the connection, our table will fill up and will have a table full with many connections that are dead. So we, in order to reuse the table space, reuse the resources, the memory, and all the resources like meters, counters, anything else we might have in the data plane for a connection, we also need to keep track of what's happening after we add the connection and remove it from the table as soon as we can safely remove it from the connection, from the connection table or the flow table, right? And now, whenever we add a new connection, we also need to ask the policy if we are allowed to do that, because we are not going to be able to add connections if the policy says otherwise. So we have some ACL tables for each direction, outbound and inbound of traffic. And the specification says we need to have five level ACL tables for each direction. And also a special shout out for this feature, which is called high availability, which essentially is looking at adding redundancy for the data plane. It's pairing up two different devices. And it's looking at replicating the flows from one device to the other device. One is typically an active device, the other is a passive device that is simply not processing traffic, although it could, but traffic is not directed to the passive device. But every time the active device is discovering new flows, is adding new flows or removing some of the flows, needs to also notify the passive device. So basically, the flows are replicated from one device to the other. It's a very complex requirement. There are also some variations where both devices are actually active and they are paired up, so things can get very complicated very quickly. But it's one of the requirements that is a must-have for many of our customers these days. So although it complicates things, although it uses up bandwidth, because these data plane devices, these two devices that are part of the HA pair, they don't have a cable, a direct connection between them. They also have to communicate and replicate the flows through the switch, so that takes up bandwidth. Now, as I was saying, there are two directions. There is an outbound direction and an inbound direction. Outbound means that traffic goes from our local VM to a remote VM. So it basically forces us to decide where we are, right? And inbound is anything that is coming to us from some remote VM, right? Now, every time, looking for TCP, what happens is usually a packet comes in, and this packet could come from a local VM or from a remote VM. We are the switch, right? Or we are the smart NIC here. And then based on the MAC address, whether we know that or we don't know that, the MAC address is associated with VM, we can decide whether this is an outbound direction or inbound. Is it coming from a local VM or from a remote VM? And that's the traffic direction that we decide. We find out very quickly here at the beginning of the pipeline. Then we want to look up that flow into our database. So let's say we have a TCP SYN packet, right? Let's focus on TCP for a second. TCP SYN is the first packet of the connection. And then whenever we are going to look up that packet and see if we have that flow in our flow table. If we don't have it, we have to we say, okay, this is a new flow. It's a TCP SYN packet. We go and we look up the policy. We ask the policy if it's okay to add this connection. If the answer is fine, okay, go ahead. Then we add a connection. But that connection needs to logically cover both the forward flow, basically packets that belong to the direction of the TCP SYN packet, but also the reverse direction. Basically, we need to make sure that we are also going to be able to allow the response of like the SYNAC packets and all the other packets coming from the other side, right? So it's a bidirectional connection. It depends on how we implement that. It could end up with two flows in the table, or could be a single flow if we do some symmetric hashing. So yeah, it's important to know that only the policy is only looked up for the first packet of a new connection. We register the packet, then we monitor the state machine for the connection, and at some point we are gonna gonna remove this connection. And now, obviously, there are some other blocks involved, like billing. We do have counters. We have overlay routing. We have underlay routing. The overlay routing is done. The lookup is done just for the first packet, and basically we store that result in the flow table lookup, right? Basically for every and for all the next packets belonging to that connection, either forward or reverse flows, we are gonna perform the overlay routing actions that we decided when we took a look at the first packet, right? Because all the packets will follow the same path through the network unless we have some ECMP involved, which is not a problem for this. So yeah, that's a very quick overview of this pipeline. Now let's look at the implementation. In order to implement this pipeline, we have our Intel IPU adapter E2100, and this some people are familiar with it. It's essentially a smart NIC, and you could look at it as like two parts. The left-hand side part over here, which is the networking part, the networking, let's say, domain, the network processing side of the smart NIC, where we have our hardware pipeline, which we call FXP, flexible pipeline or packet processing pipeline over here. So this is P4 programmable. We can create many tables, we can have actions, we can connect things together through a P4 program. Now on the right hand side here, we have an array of ARM cores. We have 16 ARM Neoverse N1 cores. And we can look at this as the compute part of the platform. And obviously we have DDR for memory, we have 3 DDR for channels, and many other engines that like encryption, inline encryption, inline crypto, or look-aside crypto, and many others that we could use, but we are not going to focus on this today. Now, the way we implemented this is somehow counterintuitive. People might think that all the packets, all the exception, or might think that only the first packet is processed by the ARM cores, and we can look at that as a sort of exception or not so fast path, like the slow part of the fast path or the exception path. That's not the case here. Because due to the complexity of the connection tracking requirements and due to the complexity of the high availability requirements, we decided to actually do the connection tracking, flow table lookup and connection tracking on the ARM cores. And then basically the hardware pipeline is going to do all the table lookups that it can do, with the exception of including the policy lookup, but it will not do the flow lookup, because there is a huge number of flows and the requirements are very complex for what we need to do with those flows. So then we do ENI and direction lookup, overlay routing, underlay routing, packet modifications, and also symmetric hashing and RSS. We use symmetric hashing to make sure that we don't have to register 2 flows and use 2 entries in the flow table for every connection. That will waste up space. And we have symmetric hashing, we have RSS here. So we use that. We play some very simple tricks to basically point the 2 flows forward and reverse to the same entry in the flow table. Also, keep in mind that the TCP state machine, for example, is shared by the forward and reverse flows. There is a TCP state a TCP state machine per connection, not per flow, right? For UDP is actually simpler. We only have to look at the timeout. Any packet could be the first packet. In order to add the connection, to remove the connection, we just have to look at the timeout, right? And essentially, we can say that the UDP connections are always in the established state. Established is a TCP state that where the data is transmitted, right? So a lot of the data path is on the hardware pipeline, the FXP pipeline, but the connection tracking is on the ARM cores. And as you could probably see, I mean, we have some SYN threads that only handle the TCP SYN packets to add connections. And we have worker threads, which are actually more threads than SYN threads at this point. And we do the TCP and UDP flow state update, the state machines, the aging part, keep tracking of the timestamps there to see when we need to remove connections. The policy lookup is also could be done here, although the main use case is to do it on the hardware part. And we also add the UDP flows here. The flow table is actually shared between these two classes of threads. And we have two instantiations of our software. In the first one, there is a global table, but lately we moved on to basically slicing the flow table into many smaller flow tables that are owned by. There is a single scene thread and a single worker thread that can access a slice of the global flow table. And it all boils down to the fact of inventing some smart data structures where you could have many threads, you could have multiple types of threads working at the same time on the same table. Some threads are adding entries in the table, while some other threads are removing entries from the table, or they are changing the entries in the table. And it's all about inventing some nice data structures that are also giving a good performance. We don't use logs, right? That's a bad word in DPDK. So that's why that's the reason I'm saying we use DPDK to make a data center switch smarter, because the connection tracking is essentially a DPDK application running on the ARM cores. Yeah, I think I'm not sure I made this point clearly. I'll make it again. All the packets actually go through the hardware fast path, but also through the ARM cores. It's not just the first packet of the connection that goes to the ARM cores. It's all the packets go through the ARM cores. The ARM cores are on the fast path, in line on the fast path. So some people might say, hey, but that's going to kill your performance. And I'm going to say, actually, on the opposite, we are going to get a good performance. So what exactly is performance? Coming to the final point, to the last point on the agenda, how do we measure performance for the Dash pipeline, for the smart switch pipeline? It's not about packet rate, it's about connection rate. How many connections per second, TCP or UDP, we can handle, right? So there is we are working closely with our friends at Keysight, and they developed a procedure. We are using their hardware and their software to do the benchmarking, and they developed a procedure called hero testing for this project, which is documented as part of the project. So essentially, they want to see what's the rate to accept TCP connections, but they also want to see that when the device is under heavy load. So essentially, we already have 30 million flows that have to be set up on the device before we start the real test. So it's 15 million TCP connections and 15 million UDP connections that are all bidirectional. And we have to pre-establish those. And then we want to play with adding TCP connections, and they also have to be removed because the rate has to be at least 3 million connections per second on top of these 30 million that we call background traffic, and they have to be kept alive. So essentially, we need to handle packets for the background connections. We need to keep them alive, otherwise they will expire and they will get removed, and the test will fail miserably. And we also need to add more connections that are short-lived, because we need to measure the rate. We have to have short-lived connections that have to be added quickly, removed quickly as well. And we use like all these XIA cards to do UDP traffic or background UDP traffic, background TCP, and also the transient, the short-lived TCP connections, which we call the CPS traffic. And you can see the details on the slide here. It's a very complex environment, and it's all focused on rapidly adding new TCP connections while the device is under heavy load. It's a very, very tough test. And this is a screenshot with performance that we get from our XIA Keysight equipment, right? And there are many things here. We take a look at some of the TCP errors or retransmissions and all sorts of errors. You see, we don't have any errors here. So it's a very sensitive pipeline to dropping packets. If you drop a packet, that packet might be a SYN packet and the connection doesn't get created, or it could break the TCP state machine if you drop a packet, or it could result in a timeout because that connection is not kept alive. So you really want to have zero packet loss. This is a zero packet loss pipeline, ideally, right? And you can see here that our rate, I said it has to be at least 3 million connections per second. TCP new connections per second. We actually do twice as much, actually a bit more. We do 6.4 million connections per second, TCP connections per second. So that's a great result on the IPU, and that is actually our conclusion. Before I take questions, that on the Intel 2100 IPU, we can achieve a TCP connection rate of 6.4 million connections per second for the new TCP connections, on top of keeping alive 30 million pre-established TCP and UDP connections. Thank you so much, and open for questions.
Hey, Christian. Thank you. Great presentation. Question about benchmarking. Is it open source? Does it require XIA, or you can run it with some commodity hardware and some open source tools?
Is this Konstantin?
Yeah, that's me. Hey.
Hello. Hi, Konstantin. Yes. So we use the XIA equipment. And there are some scripts here. Now, there are several card types that need to be used. There is this UHD, which is a switch. There is basically a single XIA chassis, right? And you have different cards. You have like Novus cards, and you have CloudStorm cards. And we use actually 3 CloudStorm cards, one for TCP background, and 2 for the short-lived TCP, the CPS traffic. And now the scripts for these cards are, I think they are open source. Our Keysight folks are open sourcing their scripts as part of the Sonic Dash repository. You can find them there. Now, can you replicate the same for, let's say, with the T-Rex or with the DPDK traffic generator? Yes, you could do that. It will definitely be more work. You have to maybe use lots of servers to do that and create your infrastructure. Now, you could devise your packet sequence for TCP, like we use just 6 packets per connection. We gracefully terminate the connection for TCP. On UDP, obviously, we don't know when the connection gets terminated unless we get the timeout. But yes, obviously, you could do that, but there are no open source scripts that I am aware of for doing that with T-Rex or with packet gen.
Okay. Okay. Yeah, thanks. And then second question, remember you showed this flow table, a table for flows, which is shared between 2 different threads, right? Between SYN thread and worker thread. Yeah, exactly. Is this part open sourced, or this yellow box in the middle? Okay.
No, this is Intel proprietary software at this point.
Okay. Do you plan to open source it?
We do have some patents pending on some of these procedures. We don't have any plans currently to open source it, unfortunately. So I cannot comment. It might happen at some point in the future, but currently we don't have any plans.
Okay.
As far as I know.
Okay. Yeah, thanks again.
Thank you.
Hi, this is Nitin Saxena from Marvel. I have a question regarding the slow path processing. Is it on OVN?
The slow path processing.
Yeah, the overlay and the underlay routing, right? It is based on OVN or what?
No, actually this is basically the overlay routing, the underlay routing, all these blocks that show up on the FXP. These are basically tables in a P4 program that is loaded into our hardware pipeline. And this is basically a P4 programmable hardware doing these blocks. And we cannot run a high-level software on the FXP hardware, but we can only run a P4 program. So we need to specify tables and actions in P4 syntax. Now you could move these blocks to the ARM cores, but then you'll use up more ARM cores. So by the way, we use 12 cores. The performance numbers that I showed, the 6.4 million connections per second, is with 12 ARM cores. I think we have 2 scene threads. 2 ARM cores doing scene threads, and we have 12 cores doing worker threads. Now you could move more stuff to the software, but performance would be lower, much lower actually. You could use open source software where things might not be as fine-tuned, and performance would be even lower again. And you are going to use waste basically your hardware pipeline. You are not going to use it. So the answer is no. These blocks are on the routing is definitely on in the hardware. It's a very straightforward block that the hardware can typically do. Many hardware from many vendors. Yeah.
Hi, Christian. This is Jarin. So this is one of the pipeline implemented for Sonic, right? Because Sonic has a lot of APIs, right? So you're not implementing all of that, right? It's just one of the use case.
Now, Sonic, are you referring to the network OS, to the Sonic NOS? There are many containers there, and yeah, that's basically one of the next steps that we are working at to integrate this with the Sonic network OS. So there are many containers there that will have to fit on the ARM cores as well, but. Also, the data path is kind of part of that network OS, including the dash, right? Now, from the perspective of the network OS, this is just control plane code to update these tables, right? So basically, you want to add routes for overlay or underlay. You want to update the policies. The control plane will not play with the flows. It might want to debug the flows, take a snapshot of the table, the connections that are in the table, but these connections are created so fast and removed so fast that the control plane cannot keep up with. So that's why this connection tracking and flow table and connection tracking is done entirely on the data path without control path intervention.
I got yes. So if you see this traditional Sonic architecture, right? They're leveraging the SAI APIs, right? So are
exactly.
you
that's what we use. That's what we use. We use the SAI APIs to populate these tables. But that's all Sonic cares about is how to populate these tables and how to sync up these tables if you have high availability, and how to do that through SAI and various RPC mechanisms that I'm not an expert of. But Sonic will not care about the data plane, right? It assumes that somebody does the data plane for Sonic. Right.
This implementation, like all the SAI attributes / all the objects were implemented using DPDK, or it's just some set of it?
Given the fact that these tables actually go on the hardware block, the SAI API that is known by Sonic actually translates to a proprietary API that we use for populating the hardware tables, right? Okay. So it doesn't go through DPDK. And now it would be great, given the work that we did in DPDK, to add the prog action for programmable devices. What we could do is we could have an RTE flow layer to populate these tables, and then use DPDK to populate these tables. And I'm pushing on that, but for various reasons it got delayed. So we still don't have RT flow. So DPDK is not involved to populate the tables yet.
So there is nothing DPDK there. It's all custom proprietary software, right? If I understood correctly. And P4, yeah, right?
P4 for the FXP, and this is on the ARM cores. Everything is actually DPDK. Well, there is also an operating system on some of the cores, but yeah, this is DPDK running under Linux, right? But it's just that we don't have this open sourced. But it's still DPDK. It's not open source DPDK, but it's still a DPDK application. Everything is DPDK API.
Okay, so then one more fundamental question. So in this use case, traditionally people use with switch, right? The standard switch, right? So, but if you're trying to do this with the DPU / IPU, right? So one is performance per watt, right, and the latency, I think these two things may not add up well, right? As a POC or doing the functional level implementation is okay, but do you think it like we can make it as a real solution if you consider latency and the performance per watt?
Yeah, power consumption is basically driven by the device rather than the application, I would say. And latency, it might have some challenges because, yeah, you have to go through the hardware pipeline, then you have to go through the ARM cores and then go back to the hardware pipeline. But that's also under control. Now, can it be real? It is actually very real because you see, like performance is telling us like 6.4 is actually double than the requirement. And 6.4 million connections per second, and that's what matters. That's what performance means for this pipeline. Is not throughput is important, but throughput is, yeah, obviously the result of how many packets you send for your TCP connections. How many packets you send them to keep the other connections alive. So you could actually do a math of the throughput that is required to get this rate. Now, obviously, in real life, the TCP connections might be longer lived, but the timeout might be also bigger. We use a very short timeout for TCP. It's actually 5 or 10 seconds for a TCP connection for testing purposes, because you want the test to finalize in a reasonable amount of time. But in real life, the timeout would be 120 seconds. So there are many things that vary, but this is not limited by throughput. It's actually limited by the connections per second you can do, and that's why basically this shines, right? If it would be an L2 forwarding application, and we would try to do this here to send all the packets through the ARM cores, then obviously the throughput would be much lower than, we won't be able to sustain the line rate, right? We will get much worse performance than if we just route everything through hardware. But that's not the point here. We don't do forwarding. Forwarding is not the main point. It's adding, removing connections very fast, connections per second. It's a kind of different mindset than the traditional L2 forwarding in the PDK, but that's what many customers in the data center want these days. So we also have to align and implement these requirements.
Okay, thank you.
Thank you.
All right, lots of good questions there. We're running a little bit behind. There's a break scheduled now, so thanks so much, Christian, and let's take the break.
follow.
people are starting to come back in. So. Let's start up after the break here. We've got enhancing DPDK performance and efficiency with RISC-V extensions from with Liang and Yue from ByteDance. Thanks, guys. Over to you.
Okay. Hi, everyone. Okay. Good morning. I'm Liang from ByteDance. So many thanks to the DPDK committees and the community for giving us the opportunity to introduce our work here. So today, my colleague Yue and I would like to share our experience with enabling the RISC-V hardware features for DPDK. Before we start, actually, there's some background to this work. As you may know, the RISC-V is an emerging CPU architecture that has been growing rapidly and is becoming increasingly popular in recent years, right? So RISC-V was initially focused on the low power user case, something like IoT scenario. However, in recent years, the community would like to expand it into the high performance computing field as well. So recently, I participated in one of their technical meetings. I just realized the RISC-V community actually have a plan to enable DPDK on the RISC-V platform. And I learned it's a quite ambitious plan. The plan covering many areas like the library optimization and the PMD optimization specific for the high-end 100 gig NIC with the vector version PMD and the testing platform selection, etc. It's very interesting to find that. And our work actually aligned well with part of their objectives. Let's start now. So this is today's agenda. So our work mainly focuses on 3 areas. The first one is the CRC optimization using the RISC-V carryless multiplication instructions. The second part is to enhance the spin lock and the power management with RISC-V ZAWRS extensions. The last part will be the cache management in RISC-V. I will go through the first topic, and then my colleague Yue will cover another 2. Yeah, let's talk about the CRC optimization here. So why CRC does matters to DPDK, right? Because I think that CRC is such an important and fundamental algorithm for the networking processing. So DPDK mainly use that in 2 libraries, as a library hash and the library net. Both of this library has the pure software implementation and also have that instruction accelerated version as well. For example, the CRC, also CRC is one algorithm, right? But still CRC has a lot of different polynomials you can choose. For example, in the library hash, DPDK software implementation choose to use CRC32C. This special polynomials actually was proven is faster in pure software implementation, but has higher probability for the collusion. But it's good for the software anyway. And also, under the library hash, there's the Intel and the ARM optimized the version with their customized instructions, like the PCL, MUL, QDQ, and the CRC32CB, etc. The same thing also in the library net. The library net CRC was mainly used for calculated CRC for the Ethernet frame, but they choose another CRC algorithm, that's the CRC32B, that's different polynomials. But also there's a shorter version is CRC16 as well. So under this two library, it's a support. It's quite comprehension for the pure software and the Intel version and the basically x86 version and the ARM version, and maybe even with in the future maybe have a more advanced parallel version as well. Okay, if we go back to the CRC algorithm itself, I don't want to take too much details for it, but just in a high-level overview, right? So simply, it's just division, polynomial divisions on the model 2. Basically, you append a bulk of the zero after the original message. The number of the zero depends on the degree of your polynomials, right? And after that, you just a long division processing. In the pure software implementation, traditional way is to use a lookup table and processing 8 bits each time. It's not really efficient. So our goal here is to improve that performance for RISC-V, because right now, because DPDK not really have a RISC-V optimized version for this, so you only can use the traditional pure software lookup table version. But we actually enable the instruction accelerated version for the RISC-V for CRC in both this library, in both library hash and the library net. Before we jump to the way how we optimize that, I do a little bit introduction for the polynomial mass, a little bit here, because all the coefficient actually is based on the Galois field, 2. Power, right? So their coefficient either is 1 or 0. So it gives them a lot of special properties. For example, your addition and your subtraction actually same thing. And also the addition and the subtraction are equivalent to the XOR. That's a very, very interesting one. The last part is most important part, is we can simplify the multiplications into just the XOR and the bit shift. And also, we can do that in parallel, so it's very friendly to the hardware. So that's why all the mainstream processor actually provide this kind of carryless multiple applications instructions to accelerate this process. So for CRC optimization, we already introduced the lookup table way, right? That's a traditional way and the most common way for pure software. However, it's not efficient because you only process 1 byte at a time. So there's two well-known, optimization method to deal with this. The first one is the Barrett's reduction. This one is very, very famous. I will do the introduction for this in next slides. Another one is fabulous method actually was mentioned in the Intel white paper. This is black magic. You basically can folding the message many times and you still get the same CRC value as well. I will introduce this in the next slide as well. Okay, for the Barrett's reduction and the chaining, this may be maybe too many maths here, but I will do some high-level summary for this. So long for short, this Barrett's reduction is to use a approximate value mu here. Okay, in order to guarantee the accuracy, we choose the k as as a 96. So that's 2 power 96. We choose the k as 96 to guarantee the accuracy. To given this pre-computed value mu, we transfer that long division into a bunch of the bits shifting and careless multiplication. Okay, let's end up with lots of bits shifting and XOR operation. But the barrier reduction only can deal with the maximum buffer size is 64 bits. So for the message longer than that, you still need chaining. So that the last formula actually demonstrated how to chain those two message CRC value altogether. Basically, you calculate the message 1 CRC value, and then you left shift that as the message 2's length, and then do XORing with the M2's CRC value. Okay, that's how to chaining that. All the black dot here, you can notice I highlight all those black dot here. All those black dot actually can be transferred to the careless multiplication instruction. So that's why that's so important for us. This one is that black magic. Intel published this method a long time ago in their white paper. If anyone interested with the greater details, I strongly recommend you read through their white paper about this. Intel basically invented a method. You can use a pre-computed constant. Okay, so most the left side, that's a pre-computed constant. Use this constant by repeatedly multiplying as part of the message, and then you XOR it with another section. For example, we do the careless multiplication with the pre-computed value with our message block 0, and then to do the XOR with message block 5, and then you generate a new message, the purple message, and you just do that for 4 times. You generate basically fold the 8 block message into the 4 block message, and this new this result, the new 4 block message still can hold the same CRC value as the previously at 8 block message. That's a magic. It's amazing, If you're really interested with that, you can go to the white paper. So I think that's why, RISC-V came with this extensions, right? Because the careless multiplication is so important for CRC and also important for other cryptographic algorithms like the EGS GCM as well. So RISC-V actually make a decision to have such careless application extensions. Its name is ZBC. For ZBC, they provide actually 2 instructions. One instruction, you can do the careless multiplication of 2 64-bit operands and producing the low half of the result. Another instruction actually produce the high half of the output. So we can use this to implement a CRC hash, and also we use this to do the folding as well. In this slide, I just try to do a summary about what we did, for RISC-V. Given this extensions, given this algorithm optimization method, what we did is for library hash, we written the barrier reduction for various of the lengths up to the 64 bits. So now the library can use the hash buffers through the chaining. Okay. For the library net, because the library net actually give you more freedom in the implementation, we actually combine the folding. We just do the 1 fold. Okay, Intel's white paper do 4 folding, but we only do 1 fold here. And this one, because we do a folding, so this one has the alignment restrictions. We combine the folding together with the barrier reduction together, because you're folding the majority of the message, and you will have a reminder after in the end, right? In the end, for the reminders, the buffers, we use the barrier reduction to processing that and to gain the final result. Because we use lots of the compiler intrinsics, so you need a modern version of the GCC, basically 14 plus or C-long 18 plus is required, okay, to compile and run all these patches. I think the patch already sent out to the mailing list a couple months ago. Yeah. Then we can talk about the performance of our implementation. So in this diagram, we demonstrate basically a pair of the CRC algorithm. One is the CRC32B and another one is CRC32C. So the orange one was the lookup table implementation for the CRC32B for the libnet, the library net. And the pink one is the CRC32C, use the lookup table for the library hash. The green one actually is the optimized version for the CRC32C, and the blue one is the optimization result for the CRC32B. You can notice that very interesting result here is for the pure software version, the CRC32C is faster than CRC32B. That's expected because you choose the different polynomial and the property is faster, but more probability for the collusion. But for the hardware version, or for the instruction optimized version, you notice that the CRC32B's performance actually is a little bit better than the CRC32C. It's different compared with the pure software version. In my opinion, that's because for the CRC32B, for the library net, we actually use folding scheme. So it looks like a folding scheme is a little bit, okay, not more, it's a little bit efficient than the purely just do the byte reduction. And here it's not really real user case because we use a bunch of data up to the 8 meg. In real life, you may not have that. May not need to do processing that, big chunk of data for in DPDK user case. However, the idea just to demonstrate, the difference between the different algorithm and the different optimization way. Okay. The second part, we just compare the G-hash performance with original pure software CRC hash function performance and the ZBC optimized CRC32C performance here. You can notice the instruction accelerated version can gain up to 4 times faster than the pure software version CRC, and also up to 3 times faster than the pure software G hash. So the blue one is the lookup table way for CRC32C, and the green one is the G hash, and the orange one was the ABC optimized version. I think this is expected. Yeah, the hardware version, accelerator version, definitely is faster. Yeah. The platform we are using here is that K230 as a RISC-V developing board. Which one actually supports the ZBC extensions. Okay, for next session, I just hand over to my colleague Yue. Yue, you can take over now.
Yeah. Hello, everyone. Many thanks to Liang for the insightful presentation. Now I will be diving into the RISC-V power management and the prefetching features, also along with some of the work we have done in this area. Okay, first let's start from 2 power-related extensions, which are zhint and ZAWIS. Zhint extension includes a pause instruction, which is a hint that indicates the current RISC-V core to reduce the instruction retirement rate. Somehow it's like tapping the brakes for the CPU. As to the duration of the pause, it is related to the specific implementation. In some typical implementation, this duration should be much less than the time to perform a context switch. ZAWIS is a more advanced extension. It is very similar to x86 UMWait instructions. It can indicate the core to enter a low power state and monitor a piece of memory in the meantime. Once the memory content is changed, the core will go back to the normal state. As to the in the low power state, it can reduce 60 to 80 around 80 power usage compared to the normal state. Okay, let's talk about some common use cases. Spin lock is a very typical scenario. Without these extensions, multiple core will keep accesses or polling a same piece of memory in a very high frequency, which will introduce severe memory contention and waste unnecessary power. These extensions can enable two complementary approaches. With the Z-hint extension, it can reduce memory access frequency by throttling the CPU by the pause instruction. Or with the ZAWS extension, it can transitioning the core to a low power state while monitoring the memory for updates with the WRS instruction. Both of them could reduce the memory contention and the power wastage significantly. A second scenario is producer ring and the consumer ring. Consumers waiting on the tail of an empty queue for the producer to queue worker or data. In packet processing case, the NIC will queue the packets to the queue or to the ring buffer. The producer may be a code executing on the RISC-V core or accelerator device or external I/O agent, etc. The third case is the code waiting on a flag to be set in memory, which will be indicated of event occurring. For example, some software run on RISC-V core may wait on a done flag and wait on a done flag in memory, and the accelerator device may indicate completion of a job by this flag. Yeah. Okay, let's start with the first scenario. For now, DPDK spin-lock library has already implemented the hint extension solution from the assembly code in red picture. We can see a pause instruction is used in spin-lock to reduce the contention and the instruction frequency. So we choose to leverage the AWS extension to implement more accurate control in spin-lock. Let's go through the process. First, we will create a reservation set containing the address we want to wait on, and using a atomic load instruction, which is the li.dw. Then we will call the ws.nto. This instruction will block the call until the reservation set is invalidated by someone else writing to the address. And then execution can also resume arbitrarily. So we will still need to check whether a change occurred, and decide whether to loop if not. Yeah. So while the li.dw instruction is called and the reservation set is not changed, the core will enter the low power state. After the memory contention is changed, the core will go back to the normal state within a very short time, which will not introduce an obvious latency. From the example code in the red picture, we can see the ws.nto instruction is used in our solution. As to the performance data, we just got hardware which supports the extension. Testing is still ongoing, and we may send it out to community in the future. The patch has been sent to the community already, and any comments is welcomed. Okay, let's as we talked in the previous slides, producer and the consumer ring is widely used in DPDK driver. Let's see how we can optimize the ring with the ZAWS extension. Firstly, let's see how it works without the extension. In the path of packet processing, dedicated call will keep polling the doorbell in descriptor. After the modified by NIC with DMA operation, the call will start packet receiving process. We can see that the before packets is coming, lots of the CPU cycles are wasted and the memory contention is introduced due to the polling behavior. Kernel driver interrupter mode can solve this kind of issue, but introduce a big latency because of the long software path. So we need to balance between the power consuming memory contention and the latency. There's already a similar implementation with Intel's UM8 instructions. In our solution, we let the dedicated call monitor the doorbell in descriptor before packets arriving. The call will run in a low power state. After the NIC modifying the doorbell, call will go back to normal state in short time and start processing packet. This part of the job is still in progress, and maybe we'll send out the patch in the future. Okay, let's talk about some cache management features in RISC-V. There are two cache-related extensions in RISC-V, which is ZigBob and demotion. ZigBob defines a set of cache management-related instructions, such as the read prefetch, write prefetch, instruction prefetch, etc. Prefetch is also widely used in DPDK. And another one is the demotion. The demotion operation moves the specific cache line from the current label to the next label, from the current cache label to the next cache label, rather than executing it completely from the system. So this is important for data sharing and cache coherence maintenance in some multi-core systems. But demotion is not widely used in DPDK for now, so we haven't enabled it yet. Okay, for the ZigBob extension, on modern versions, such as the modern version of compilers, such as the GCC over 13 and the Clan, use the built-in prefetch already. This will generate the RISC-V prefetch instructions. So which means that you don't need to do anything to use the prefetch functions in RISC-V. But if you are still using some older compiler, that's the problem. To solve this, we have added a new flag, which is the RT prefetch write defined. That is a little similar to RT wait until equal defined flags. It will help to hide the generic implementation of the RT prefetch functions. So you can use the RISC-V related specified prefetch functions. This patch is also sent to the community. Okay, that's all my presentation. I'll give back to Liang.
Okay, many thanks, Yui. So what's next? Yeah, so you can see most of the patch already sent out to the mailing list for a while. So we are keen to seek, more reviews, and we really want to push the patch forward, right? Because with RISC-V community and the DPDK community can collaborate together, and to enable RISC-V on DPDK smoothly. Hopefully, those patch can be merged in the future. But we definitely need more review and more feedback for all those patches. The second one still actually is the approach for RISC-V extension detection at the runtime and compile time. That one's still open for discussion. The reason for that is the RISC-V community actually came up with a different way to allow the user application to query the extensions. Instead of by using CPU ID, the traditional way DPDK use, they actually came up with a system call that's a RISC-V hardware probe. It's a new system call only working for the new glibc and the new kernel, to use that to complete the extension detection. But that's actually some open question, right? You can use that way, you have a pro and the cons, but if you don't use that one, also have some problem as well, for specific for the old kernel and the old compilers. So this one actually still is open for discussion. But also inside our patch, we already use that system call to do the extension detection. But yeah, we really happy to see more discussion on this. This is quite a general problem, not just for DPDK. I think lots of other community like Golang and Java, they actually have similar problem as well. Most of them accept to use that system call. Yeah, we really would like to have more opinion on that. And in the future, we may to investigate some potential of using the vector version of the careless multiplication instructions, like the vector, CL, MUL, and to enable greater, parallelization and improve performance even more, right? But the problem is that we really need waiting for the hardware actually support those new extension version. The final one is something we are working in progress with the moment. So we just got some platform support the ZWRS, so to testing all those ZWRS extensions in the hardware. Okay. At the final, at the last, we have to thank a lot of our friends and colleagues to contribute, to this work. So Daniel made significant contribution to this work. And the Ponit and the Chunsong also offered lots of help with this work. We have to thank all of them. Okay, the final will be the Q&A. If anyone have any question, and yeah, we can try to answer it. Thank you.
I think we got one question here. Yeah, go ahead. And we'll go over.
Yeah. Before having the technical questions, I wanted to ask about you, especially the ByteDance, right? So this RISC-V platform, how important it is to you? I know this RISC-V, RISC-V platform is pretty much like open source and rapidly growing. But how, in terms of your business, how important it is to support that?
I think, okay, first of all, that's not a technical question. And I personally, okay, as a company, I think I may not have any comments on that. Personally, I think I will see the RISC-V really is, emerging and, became more and more popular, right? So lots of companies actually have interest in with that. Even NVIDIA, have lots of interest in with that as well. And Qualcomm, so many companies actually have interest in with that, not just ByteDance, right? I think that's generally interesting, and we also love to, support the community and upstream our work here. I think that's all I can say. Yeah.
Okay. Hi. I have more of a curiosity technical question. You mentioned you were discussing the wait operations on the memory. And do you know, are those instructions that wait on the memory change have an acquire semantics, or do you need an extra memory barrier or an extra acquire read from memory in order to ensure the memory ordering? Like, since this will be important for the consumer producer rings and spin locks and stuff like that, for all the previous memory to be already available? Or is it even not a problem for RISC-V? I'm not an expert in RISC-V, so.
It's fine, yeah. In my opinion, okay, maybe you is better person answer that, but in my opinion, there's no memory order consideration for that, because that actually is for, basically it's waiting for invalidation from the either ring bus or mesh, whatever, underneath, right? Because RISC-V not really is it's just instruction. definition. It's not really a silicon implementation, right? The underneath implementation still heavily depend on vendor, you know.
Okay,
So for example, if the vendor implements that their memory order is weak, really weak, and really relaxed, might need some extra action. But if the vendor implements their memory order like have strong order, you may not need to worry about that at all. You know, personally, I view things as vendor specific.
Okay,
That's
but
my answer. Oh, yeah.
Okay, but if we are implementing this, like basically hand rolling some of those stuff or some of those instructions in the DPDK code, then we need to be aware of what's your underlying hardware,
yes, for
right?
sure. Yeah, for sure. Because we are okay. To be honest, RISC-V is a little bit fragmented, right? There are so many different RISC-V product. In the platform we are working on this moment, we still try to do the performance benchmark to see, and also testing as well. We didn't see any problem so far with memory order. Okay, but we definitely will take care about that because it's really is platform specific in this moment. Maybe in the future, they will have more unified, behavior. But right now, personally, I believe that's really platform specific, vendor specific stuff.
Okay, thank you.
All right, we're still running a few minutes behind, so let's thank the guys from talking about RISC-V.
That's everyone. Thank you. Bye. Yeah.
Thanks, guys. And up next, we've got build system design for ARM platforms.
Yeah. I can't see my. Okay. Yeah. So this is a very short talk. I'll try to keep it short. It's about the build system design for ARM platforms, which has been around for a long time in DPDK build subsystem for ARM, but we did some changes recently. And maybe there are some confusions, and trying to explain the design philosophy behind those choices. So, my name is Vatsala. I'm a software engineer at ARM, and as you can see from the names, Honappa was also involved in this change. So the motivation for this change was actually based on the fact that ARM is fairly diverse in terms of ISA versions, architectural extensions. If you look at the Meson build file for ARM, you would see these ISA versions and extensions used widely by different SOCs. And then to make matters even more complicated, we have different kinds of vendors. Some are interested in highly performant builds, and some may not be that interested in the performance. They may try to make it more portable, like, for instance, distro vendors. So, as I mentioned, these highly performant builds, which are preferred by SOC vendors and appliance vendors, kind of tuned for a very specific ISA version, and they may also have a set of architectural features that they may want to use with that build. And on the opposite end of that spectrum, you will find the portable builds people who value the portability. They might want to have some kind of a good out-of-the-box experience of a particular build. So they may focus on the portability. Mostly Linux distro people, they are the ones who are kind of interested in this approach, right? And then we have three kinds of builds that we try to push to address the different crowds, right? So the first one would be the generic one, which is kind of very simple. It's for portability. And you can also fall back to generic if the GCC version that you are using or DPDK lacks support for a particular CPU. You can fall back to generic. It's pretty simple. You pass dplatform equals generic at the build time, and then it will generate like that argument will get translated into mark equals ARM v8a plus SIMD, which means generate a binary which works on any ARM v8a and below plus some neon extensions. So this is the most portable one. Any 64-bit ARM CPU out there would understand this instruction set, whatever that goes into that binary. And the next one is SoC specific. Why we need this? It's because we care about, some people care about performance, as I mentioned. If you are a SoC vendor or a appliance vendor, might want to have some performance benchmarks out of that build, and then in that case, you will want to build it against a particular SoC. So the caveat here is that it should be supported by the version of GCC you are using, because we are relying on the MCPU flag. So for instance, if the GCC version that you are using does not recognize that particular MCPU, or the CPU name, it will fail. So that support needs to be there, and also DPDK's ARM build subsystem should understand that argument. So for instance, in this case, I'm using V2 as an example. So if you pass dplatform equals V2, that's going to build a binary that works on Neover's V2 line of CPUs, right? And then we have the custom builds, which are kind of in between, I would say, because there might be folks who need performance, but at the same time, the GCC, the latest GCC version may not recognize that particular CPU. For instance, like up until GCC 15, the V3 and N3 CPUs were not recognized in MCPU argument. So we had to use this custom build option. So here, what you're going to do is in the Meson.build, you have to define a MCPU version, which is basically made up of, we call it a pseudo MCPU. You can call it a pseudo MCPU. I'll show you how one could generate this. So you can specify the base ISA version, and then the set of extension that you want to use, and call it, let's say, foo, and you pass dplatform equals foo into this build, and ultimately the build system will generate mark equals the ISA version you gave plus the list of extensions. So that way you don't use the MCPU, but as the person like who's basically as an expert, you may know the ISA version and everything that particular CPU supports. So this is actually how you add a SoC specific build to the Meson.build. So let's, for the time being, ignore the box 0 and focus on box 1. I'm using NVIDIA Grace as an example for this. So you start by defining a SOC. Now SOC Grace has a part number, which is a hexadecimal value, D for F. And this part number is unique to a Neoverse V2 CPU model, right? So then it refers to a part number definition in the part number config space, and it says that MCPU that you're supposed to use with this particular build is Neoverse V2. And then these flags, you can ignore these. These will be passed into the build as macros. But it also specifies some extra features, some features that are unique to this particular SOC, in this case Grace. It is crypto, right? So once you have this definition, you have to give it a short name. You add that to the SOC's dictionary, and the name is Grace, and it refers to the SOC Grace definition. And then in the build time, you pass the parameter, the platform equals Grace, and then the build would generate this MCPU, the red box, in the build time and pass this to GCC. So what's going to happen now is that the binary will use the ideal ISA version for Neoverse V2 with the crypto extensions, right? So it's confusing because it's a little bit different from x86 Intel definition of MCPUs, MTune, and all these other things. So ARM uses a different convention, I guess. Now, if you want to do a custom build example, it's almost the same. Let's look at the box number 2. In this case, it's I think Thunderx 2. It does not have an MCPU defined, so we'll have to add a custom build SOC. So you define the SOC. Part number for that particular CPU is here, which is hex AF, which is referred in that line, and then you have the definition in the part number config. Now, if you look at this MCPU, it does not really exist. So it is a like a pseudo MCPU which you define much later in that MCPU def's direct dictionary, right? So if you look at the MCPU def's dictionary, it defines MCPU underscore Thunderx 2 T99, which I think Marvel knows what ISA version it supports. So according to them, it's V8.1a, and it has a bunch of extensions, CRC and crypto. So ultimately, when you pass this argument, dplatform equal Thunderx 2, it's going to generate that mark. Since it does not have an MCPU defined in GCC, it generates that mark equals ISA version plus CRC plus crypto, which is the optimal binary for that platform. So we have a couple of these things. So there's one caveat here. The moment a GCC compiler version starts supporting this CPU, then you have to remove this content in box 0 and use the proper MCPU. So you don't have the custom definitions, like kind of no use of it after that, right? Yeah, that's it about the build. With that, we'll move on to questions and answers.
Related question. Suppose I use a specific, build architecture, right? And how do I verify it? Is there any ARM tool to verify Argparse tool or something that will tell me that it's running better?
You mean verify means you have the binary and you want to make sure that it supports a particular.
Yeah, I compiled with certain architecture, right? And I
Yeah,
have to run a tool, and I can see that okay, this one performed better, or is it just that in the code there are specific machine architecture in a specific code that changes the binary itself?
Yes.
But I want to see the difference, right? How do I verify the difference?
So a lot of times the ISA versions, the difference between the ISA versions is the instructions. So let's say V8 has a set of instructions and V9 has all the instructions that were in V8 plus some extra instructions. So those extra instructions could be like SVE, SVE2, all the advanced SIMD instructions, and there are a bunch of other things like now we saw some RISC-V wait for event kind of things. So all those things we have in ARM as well in V9, but in V8 you may not find those things. So one way to verify is that, for instance, you want to use wait for event with a timeout. That instruction is only available in ARM V9 ISA, right? So if you build DPDK for that particular SOC, some SOC that uses V9, then it will emit those instructions in your binary. If you do an object dump or the binary, you would see those instructions. But if you build it for some other ISA version, that instruction will be not there. It will be replaced by something else. It's like that. So there's no tool per se, but you can manually do the verification with a tool like object dump, which comes with GCC, I guess. Does that answer the question?
There's some code that's not with is small source, right?
Yeah.
Basically some cases using some specific instructions that have a different flavor, different path, different number of different
Yeah.
right? So I'm aware of it, so I just want to look at every code, right? So
Yeah, typically if you ask the compiler to use a particular instruction set version, it's going to enable those things. So, yeah.
Hi.
Yeah, we have perf. Like it's it's basically the performance counters. They also change from one CPU to another, right? Say, for instance, N1 may not have all the counters that are available in N3, and then we also have other counters which are off-core on the interconnect. So you can use perf to measure all those things.
I don't have a question with respect to the ARM architecture per se, but in a DPDK, whole DPDK build system wise, to the DPDK maintainers actually. The point is that right now in DPDK, the build system is compile time, so you expect that the application will always compile the DPDK, but there are some open source projects which compile the source code for multiple architectures and runtime select it. VPP does it. It's a multi-arc select feature. And it is needed when the DPDK is being released to the distros and the application is linking to the distros, right? So at the runtime when the shared object is being loaded, the correct architecture-based compilation binary is being selected. The functions are being selected. So is there a roadmap for that? Because I was talking about it to Jaren and he said DPDK does not support it.
Yeah, right now we don't have anything, and I don't think there's anything in the roadmap either. For distros, like for instance, it's a generic build at this point. So if you do a 64-bit distro, then it's the D platform equals generic. It will generate the V8 instructions.
Okay, cool. Good discussion and maybe a breakout session this afternoon. Over to Nitin to give us a talk on RT graph. And by the way, we're trying to locate a second mic, so if anybody's got a mic on their table, please let us know.
Hi, my name is Nitin Saxena. I work as a senior principal engineer in Marvel Technology. And I'm here to present RT graph feature functionality called feature arc. Little about my experience. I've been working in Marvel for the last 14 years. I've been using DPDK for the last 6 to 8 years, but I haven't worked on it directly. I have worked extensively on VPP. Now, recently, I started with the RT graph library. 1 minute. So, if you have to ask me in a simple term what this feature arc is all about, then I will say this. It's an abstraction for a RT graph-based stack to add runtime configurability, node reusability, stability, and packet path overloading. So what all the keywords I have highlighted here, I will just try to explain in the subsequent slides. So regarding the network configurability, this is the most important features RT graph. So feature arc is trying to bring in RT graph library where the runtime protocol updates can happen. Not all protocols, if you have more and more network functions in the stack, not all protocols will be enabled all at once. You will enable only those protocols for corresponding to the network functions for which the stack is configured to. And among all the protocols being enabled, some of the protocols needs to be enabled at runtime, like you're running a router and then the strong swan daemon comes up, then the router has to act as a security gateway. So the protocols are being enabled at runtime and they can be disabled at runtime, not just one time, multiple time. So the design has to take care of that there is a control power plane and the data path synchronization is happening. So that's the runtime control plane path. So in some network functions, there are some protocols enabled in a same networking layer. So if you have a firewall, then you could have IP tables, IPsec at the IP layer, and there has to be a protocol processing order that needs to be defined because packet has to traverse either to one of the protocol, right, among those three. So the stack can decide that, okay, let's have an IPsec decryption first in the ingress direction and then IP reception. And then in the egress direction, you can say do the IP forwarding, then IPsec encryption, right? So we're talking about the two protocols here, but even in the case of ingress and egress direction, the ordering sequence is different. And we can also have IP table protocol, which application is determining where it's saying that, okay, add the IP table before routing or the post routing. So that capability should be there, and Linux supports it. So we have both the use cases available. Who is deciding the protocol processing order? Now, third thing is that, third thing is that we have to understand that how the network protocols are being configured in a typical stack, in a typical stable stack. Some of them are being enabling on the interfaces, like port-based IPsec is one of them, IP reception is one of them. Some of them are with routes, like route-based IPsec is there. Routing is a functionality of route action. Flows, whole OVS, and is software-defined networking based on flow index. Classification rules. I mean, the QoS, Juniper guys have described it that based on the classification, the QoS can be, protocol can be selected. So feature arc works on an index which tries to cater all the network configuration possibilities within the stack. So it works on the index, whether it is interface index, route index, flow index, anything it can be. So node usability and stability comes as a byproduct from the feature arc, because we would like to promote in RT graph library that application should not duplicate the DPDK enabled nodes. Over time, we would like that the standard protocol nodes are part of RT graph library, RT nodes library, and application should have only the nodes which are application specific to the application, and they can just hook their custom nodes, the application nodes, to the inbuilt protocol nodes which are presented as part of RT node. The benefit will happen that over a period of time, the inbuilt nodes will become stabler because they will be tested against many network use cases, and they will become more RFC compliant over time. And then what we have to do is just that the interfacing of connecting the application node with the RT node should be very simple, and feature arc tries to do that. I will explain it how it does it. Packet path overloading is another way of saying node usability. Each network function has a default node packet path. So when you say it about IP routing, it is like get the packet, do the IP reception, send to the lookup, rewrite out this default node path. But then there can be in a suricata like application which says, okay, let me do the IP filtering in the ingress path or do the IP filtering in the egress path. So we would like to have we'd like to add a capability such that the default protocol nodes are present as part of RT node, but application is able to overload that node path also. Last, performance and latency. Feature arc does not stop the worker course when the runtime network configuration happens. It uses RCU mechanism to synchronize the control plane data path, but it is not required. Only in the corner case it is required. Little bit about RT graph overview, those who don't know about it. So RT graph is a design, a framework in which the bigger protocol is being split into small functions. Each function act as a node, the graph node, and each node goes over the burst of packets and try to perform the small task. So each node tries to leverage the Dcache and iCache benefits of the microprocessor. So that's the benefit of RT graph architecture. The point I'm going to try to highlight here for the sake of this presentation is each parent node in the existing graph library, each child is connected to its parent with a predefined edge, which is compile time. So, sorry. So IP6 input is, if you see the third row, IP6 input is connected at the 0th edge of ith input. IP4 input is connected at the first edge of the input, and the MPLS input is connected as a second edge of the ith input, which is good. It gives the fast performance of the graph traversal, but it adds a point of rigidity in the graph. So why it does it? So if you see at the line number 25, line number 29, the node X is saying, node X is the parent child, it's saying at the 0th index, 0th edge, node A is added, and on the first edge, node B is added, and at the line number 19, which is the process function of the node X, it says that, okay, the edge is hard-coded, so it is, there's no room for adding any kind of overloading or dynamism here. Feature arc is trying to add the flexibility here. So I mentioned that predefined nodes are fast, but they lack the flexibility to overload, and feature arc tries to add the child to the parent at runtime, not at the compile time, and the edges are being maintained by the feature arc. Coming to the main topic, feature arc. So why the name feature arc? It is the abstraction which is similar to the abstraction in VPP, named as VPP feature arc, and is try to bring in the same functionality what is present in VPP. So feature means protocol, arc means protocols are being arranged in an arc form through the edges. So that's why it is the order list of protocol nodes. In order to create a single feature arc, we need two objects essentially. One is start node and end feature node. Start node and end feature node can be anything in the graph, pre-existing or new one. There's not an issue. So feature arc is actually a hook point in the graph design. We can have n number of feature arcs. There is no limitation of it. Once the feature arc is being defined, then any number of feature nodes can be added between the start and the end node. So feature arc is a high-level abstraction which allows developer to implement the relationship between the multiple protocols at a given layer. But in the fast path, what it is trying to do is it is just trying to give an edge, the edge of the next child from the current parent. This is what it is doing. So I will just go through the fast path APIs later. So how to use feature arc? So top threes are like control plane APIs, registration of feature arc and feature, which is constructor-based, feature arc library initialization, just a single initialization library, enable disable of the feature, and then we'll go over the fast path API usage. So regarding the feature arc registration, so if the arc has to be created for node X and node Y, and node X and node Y are already present in the graph work, let's say in this current application. So node 2, so line number 2 and 3 saying that node X and node Y are already defined. So the arc can be created, very simply it can be created at line number 14, which says the name of the arc, which is arc1 output, it can be anything. It tells that it takes the max index argument, which says that on how many index it want to operate on. So right now it is saying, okay, this arc will be working on physical ports, which is RT-matrix arc ports, and then it takes the start node pointer, which is pointer to the node X, and end feature node I will cover later in the next slide. And there is a start node feature process functions to be provided. It's a duplicate of what is being provided into the RT node registration. The reason being, feature arc is being added as an optional feature, and some application may be not using feature arc. So if the feature arc is not initialized, then the original node process function will be called. If it is initialized, then the function which is provided here as a feature arc registration will be called. And once this graph architecture is being defined, the constructor can be called, which is RT graph feature arc register, and that's it. This will allow to this definition will allow you to represent node X and node Y, which are connected with each other. But nothing will happen right now until you do not call the feature arc init API. So now in this slide we have created the arc and connect the node X and node Y. But if you want to add any feature node, and this feature node A can be inbuilt node or out of tree DPDK. It's possible. So only 8 lines are required here to add any out of tree node to the existing arc. So the feature registration just required the name of the feature, arc name to which it want to link to, and the feature process function. It's same as what I explained earlier, and the pointer to the node A, and then just feature register. This is the simple interface with which the feature node A will be required, will be added to the arc. So now I would like to go over certain advanced parameters of the feature registration. So we are trying to add 2 more features, feature B and C. But here, if you see line number 19 and 20, the feature B is saying let's go over to the feature C first. So feature C is saying, okay, add me after node A. So at line number 10, it is saying node C should be added after node A. And at line number 19 and 20, it is saying that node B is saying add me after node A, but before node C. So it exposes to represent a relationship between the protocols, if there are any. Few more things. So at line number 11 and 12, there's a notify callback whenever a feature is enabled or disabled. The notify callback is called with, I will explain it later, point of time. So I have also added something called override index callback. If you have remembered, the feature arc is being registered with the maximum it's created with to operate on physical ports only, but certain feature is possible which would like to extend that capability to virtual interfaces also. So any feature out of tree or inbuilt can return a higher value than what feature arc is, what value is being provided to feature arc, and the feature arc, and then the feature arc will be created with the higher value. So that's override. It is to every feature this capability is given so that it can override the index. So far, feature arc and features registration has happened. Those are just construct bits. No memory has been allocated. Nothing has happened until and unless application will not call the RT-graph feature arc init API. Only when the application calls the feature arc initiation API, before it has to be created, it has to be called before RT-graph create. Only at this point only the feature arc will be created. All the childs will be connected to their parents, and all the relationship will be created at this point only. If application don't call it, feature arc library is a knob to the application. So once the feature arc has been declared, the feature arc is initialized, and the graph is being created. It has entered, the application has entered into the RT-graph walk loop, and at runtime, these APIs, feature enable and the feature disable APIs can be called, which is corresponding to enabling any protocol at runtime or disabling any protocol at runtime. It takes some parameters. 1 minute. So it takes some parameter. One is the arc object, and then in the index, on which index it would like to operate on, and the feature name, which is node A, feature node B, whichever is would like to enable, and a cookie is to be provided, and cookies will, and then the RCU. RCU parameter is an optional parameter. Now cookie, so a little bit about cookie. So let's assume you would like to enable a IP routing for a interface 0. Now it is possible application can create a fib table 1 for interface 0. So it means with the input VRF. So it can allocate a VRF resource, assign, provide that cookie, the VRF index into as a parameter to as a cookie. Now the fastpath API, in which will get from the MBUF. It says, okay, MBUF is coming from interface 1. Then the cookie is passed to the fastpath API. And then with respect to that, the lookup can happen. The feature node can do its local lookup. So that's the point for the feature and enable disable API. So if you see here on interface 0, trying to enable feature A on interface 0, feature A on interface 1, but on feature 2, I'm trying to enable feature B and not A. So in the fast path, if you will select, give me the first feature enabled on the interface 2, it will not give feature A, it will give feature B on the fast path. And you can disable also from the control pane. I think the font size is small here, but start node packet traversal, the rule is very simple. The predefined nodes are being used to transmit the packet as a default packet path. But if there is a feature enabled, which can be enabled at runtime, because control plane is updating, can enable any feature, then the edge, I don't know if it is visible, at line number 21, there's an API called feature data, first feature get. It overloads the edge, and then at line number 20, the overloaded edge is being enqueued. So that's the rule that, okay, continue to work using predefined nodes. If there is a feature enabled, just overload the edge and enqueue to any runtime feature which is enabled on a particular interface, which is MBUF port is being passed as an argument here. So the fastpath APIs are different with respect to whether they are being called in the start node or in the not start node. In the start node, as I explained, the traversal rule is like, okay, if the feature is enabled, then just send the packets to the feature arc path. But in the nodes which are being added as a feature, because the node is called, which means most likely this feature is enabled, and what it can do is, it can, so let's assume this is, I explained in a previous example, let's say routing node and VRF has been created in the control path. So at line number 20, it says, okay, give me the app cookie for specific to the feature which is routing, and the interface is MBUF port. The VRF table will be retrieved by the app, it's a 2-byte app cookie, will be retrieved. The local lookup can happen at line number 22, it happened. If the current feature is can drop the packet, it can consume the packet, it can send to another node if it wants. If it don't want to consume this packet, then it should send to the next enabled feature, which can be anything this node is not aware of. So it should call this API RT-graph feature data next feature get, and the edge will be overloaded, and it should just enqueue it to the, it just call the standard API. This node should not be aware of, should not need to be aware of which next node is being, which next node is enabled on a particular index, and it is pretty generic. Yeah. So I have talked about start node, the feature nodes which are adding between the start node and the end node. Now there is a rule for end feature node also. There should not be any fastpath API to be called in the end feature node, because it is a sync node through which the packet exit the feature arc. So end feature node, I forgot to explain that when a particular feature is disabled at runtime, the packets are not dropped, they are steered to the end feature node, so that they can exit the feature arc path. So I explained the enable and disable API takes the RCU parameter. Most likely it is not required. The feature arc APIs are thread safe, but in some condition it may be required, where there are some corner cases, like application is doing enable disable in a for loop, which is not a valid use case, but in that case may be required RCU. The RCU is also required if the certain resources has been allocated by the application, like I explained, the VRF table has been allocated by the application. Now it would, so when the feature at point of feature enable, now after feature disable, when it is trying to disable the feature, the allocated resource needs to be released, and when it needs to be released, application should be aware of that no worker core is accessing that data structure. So for that mechanism, RCU is required so that it can make sure that that the no worker, when it is freeing the data in the notifier callback, no worker is accessing that data structure. So performance impact, because so compared to the top of the trunk DPDK, which does not have any flexibility, it works on the compile time, there is a performance regression because we are trying to add flexibility in nature. So I have added one feature arc as part of a patch I pushed to the upstream. So if the feature arc in it is API is called, initialization API is called, but no feature is enabled, there's a drop of 0.17%. But if there is a feature, one feature is enabled on an arc, and then extra node is being called. So let's say in the routing network function, there are 4 nodes, and you enable runtime. You enable one more application node. Let's assume. So right now there are 5 nodes being executed. So there is a performance regression of 5.2%. This is what it is, but it comes as a cost with the flexibility. Feature arc constraints. The only constraint is that I think there are few constraints are that the feature arc initialization API should be called before graph create. Enable disable API should be called after the graph create. To a particular feature arc, only 63 features can be added. If you would like to add more features, you can have more number of feature arcs. There is no limit to number of feature arcs. And feature nodes are not being shared among more than one feature arc for the performance reason. I deliberately didn't do that. We can add it, but it is not required for the performance reason. Follow-up, we got the initial feedback from Red Hat, Robin and Christoph and David. So I have tried resolving their comments. I have pushed the patch to DPDK 2004. I have 2507. So please review the patch. As part of the initial patch, I have added the IP4 output feature arc, which is the first hook point in the IP4 egress path. More hook points as a feature arc can be added. Yeah, that's it.
Here already, I'll stop with Constantine.
Okay, thank you. Hey, one quick question about performance numbers. So you showed it's about 5% degradation when one feature node is called, right? And what would happen if you have, as your example, 3 feature nodes? Would it be linear degradation, or this is just the maximum?
No, it's going to be linear degradation because, so that's why feature arc is not being added on all the nodes. It will be added only in the designated nodes like IP4 input, IP4 output, IPv6 input, output, okay. IP4 punt, local. So there are designated nodes because, so just assume like a net filter in Linux kernel, right? The way it tries to give you hook point, right? Same thing, this feature is trying to add it in the graph design.
Okay. Okay, yeah, thank you.
Thanks.
Thanks.
Hey, Nitin. Thank you. Presentation was good. I have a few questions. The first one is, does the infra provide any way to detect cyclic dependency during the features A calls B and then B again tries to call A kind of a thing, so packet keeps looping?
So you want that functionality or not?
No. Does it have any defensive mechanism to have?
Yeah. So RT node already have it. So you cannot have A. No, I think RT node does not have it. A to B and B to A. You can add it. No problem.
So the packet keeps kind of looping, or how does it? Okay.
Which is not part of feature arc, it's already part of RT node, RT graph, sorry.
Oh, got it. And you mentioned there is a cookie, right? So is this the packet context where it says...
Can you please repeat your first word?
There is a packet cookie, something you
packet
mentioned,
cookie,
right?
yeah,
So
correct.
that is a context for MBUF, which says like, which is the previous feature, what was the VRF?
Yeah,
things
so
like
sorry,
that.
I forgot to miss that. There is a dynamic field registered for the feature arc, and within the MBUF, that dynamic feature is being propagated through the graph traversal. And because of that, I'm able to manage what is the next enabled feature.
Oh, the dynamic field, okay, got it. And in this slide, right, the performance, you said like 5% degradation, right, per feature. Is it, because...
No, yeah, go ahead.
So is it because of the infrastructure like graph traversal, or is it because the feature itself is adding the extra overhead?
So first of all, there is an extra node is called in the second row. So the graph walk is being calling, and then the extra node is being called. And so the extra node which is being called, it is fast. So I'm just using the mem-move API, which is very fast. And then the feature arc data, feature arc penalty would be much lesser, I believe. But there's no point showing only the feature arc point, right? That I cannot show that. That's not practical. So that's why I said, okay, let's take, this is the maximum penalty you will get once you enqueue to the single node.
Okay.
Yeah. Oh, so it is not doing anything. It is just get the packet from the stream and then just do the mem move. It's very optimized.
Okay. Yeah. Thank you.
All right. Thanks, Nitin. Next up, we've got Robin talking about Grout.
Okay, if we can test your audio and get that screen share going here.
Hey everyone, so I hope everybody can hear me fine. I'm sorry for not being in Prague with you. I wish I could have, but unfortunately it was not possible this year. Today I'm here to talk about Grout, which is a DPDK hosted project since last September. Before starting this, this is me. I work at Red Hat in the OpenStack NFV integrations team. Here's the agenda for today. So for those who missed the talk in September, I will give you a summary of what is Grout, and then we'll give more insights about where the project is today, and then we'll dive into some highlights of of how it's built and some of the new features. I'll try to give you a short demo and try to see where we're going with that project. So for anybody who missed the talk we gave with David last year, I'll put some links here. Hopefully the slides will be uploaded on the talk later on today. So what is Grout precisely? So initially we wanted to have a vendor-independent software router. So we want something to be able to replicate whatever VNF or CNF that we need to run in OpenStack or OpenShift. We want to have something generic, which isn't tied to any specific vendor. We wanted that project to be strongly tied with DPDK, and we wanted so it could be used as a I don't want to say flagship project, but something to bring more visibility for DPDK libraries and drivers. And also, we made absolutely zero compromise on the design of the stack. So it means, I will explain that later on, but it means that Grout, the graph, the packet graph is really strict with what nodes are allowed to handle based on the stack level where we are in the stack. I will explain that later on. It has a way to, so you have a API with a Unix socket where you can exchange messages in order to program and configure Grout. Obviously, it's completely open source. There's no, yeah, it's open source, right? And as I said, it's a hosted project. So where did we start last year? So in September, we had V4 and V6 IP forwarding, multiple VRS. We had some VLAN support and a proof of concept for IP in IP V4 tunnels. Since then, we have made significant progress on multiple fronts. So since February, I think, you can actually DNF install Grout on Fedora. We added a bunch of debugging tools in order to trace packets, and also you can enable packet logging dynamically. You can dynamically move the data path threads from one CPU to another without restarting or anything. We have a way for packets entering DPDK interfaces to be sent to Linux. For example, if you want to have strong SWAN or FRR integration, you can actually have inline BGP traffic terminating on BGPD, but the packets will go out DPDK port controlled by Grout. We also added the L1 cross-connect mode, which is similar to test PMD in IO mode. We added that because at Red Hat, we have internal tests where people were using test PMD, and we try to make them move to Grout. And since the L1 cross-connect is exactly the same as test PMD IO mode, it was simpler to start with that and then move to IP forwarding. And also we got the segment routing based on IPv6 added by an external contributor this year, which is quite exciting. And So where are we going? So right now there's a FR backend plugin which is in progress. It should be probably ready at the end of this summer, I think. We'll also be working soon on a stateless NAT node. So we'll start with DNAT and maybe we'll do source NAT, and so that will involve connection tracking at some point. And also I wanted to highlight some that graph pipeline mode for slow path handling. Maybe this is something we can talk about during the Q&A at the end. I would like to challenge the guys at Marvel about how we could go with this. The idea would be to have packets being handed to other CPUs for slow path handling. So for example, when you receive an ARP reply or request, instead of processing that in the data path, you would want to send that to another CPU so that you can continue processing other packets at high speed and let the control plane CPUs handle that. But so for now in Grout, we kind of need to send the packet out the graph to be handled differently, and then it needs to re-enter at some point. So we would like to have something more integrated, and so everything stays in the graph. Let's go on. I'll give you an overview of how the packet flow is handled in Grout and how we manage the network layer separation between nodes. Also, we'll see how the graph looks like today, and we will have some quick look on the new features that are landed recently. So this is basically a simplified view of the IPv4 graph. So what happens is that we have layer 1 RX node, which iterates over every port plus QID that we have. And it will resolve which interface, logical interface, is associated with that port number. It will then send the packet to Ethernet input, since now we only handle Ethernet. And the Ethernet node will pop the Ethernet header, possibly the VLAN as well. And it will send the packet to IP if the Ethernet prototype is IPv4. Otherwise, it will send it to another node. This is done dynamically without jumping back to the previous talk, we started this work before feature arc was introduced, and we found other ways to dynamically register nodes based on another mechanism. Maybe that's too technical dive for today, but maybe we can talk about later. So in IP input, now we have shifted the mbuf offset to the layer 3, and we can do a route lookup based on the receiving interface, which gives us a next hop. And then while at layer 3, we can do TTL decrementation and recalculate the checksum. And then based on the next hop we got in route lookup, we can determine where we need to send the packet. And then, so at that point, we can push a new Ethernet header with the correct destination and source. We can push back the IPv4 Ethernet Ether type and then transmit the packet on the correct port. Right. So this was in September, the graph with the highlighted path in yellow, like this. So it was pretty simple. I have excluded all the error nodes. So this is the simplified view. So, and this is today where we are. So it's a bit more significant. At some point, we will need to stop displaying these graphs, but because I think it will become too complicated. But anyway, so as you can see, there's a lot more control operations happening. And this is what I was referring to when I talked about pipeline mode. So everything that needs to be handled by the control path is sent to control output. And then when the control plane wants to inject packets, it needs to inject them in control input. So ideally, we would need to have a better integration with the control plane CPUs or workers. But for now, we deal with that differently. So yeah, so this is one new feature. We can be handy when you're trying to debug where the packets is being dropped and why. So every node has a way to attach tracing data. So it's basically just a byte buffer that you can pass. And it's stored per mbuff. You have some sort of linked list of tracing data. And when the packets is transmitted or dropped, the tracing information will be stored somewhere in the ring. And then via the API, you can access all this traced information. So I've displayed a short example below where you can see the packet entered port 1, Q0. Then the Ethernet input node added the Ethernet header information. Then in IP input, we saw something about the external IP addresses. And then we see that the IP protocols was IP in IP tunnel. So the packet went through IP input, and it actually popped a tunnel. And then the packet was re-injected into IP input with a different IP address. And then the packet was forwarded and then transmitted to port 0, Q0, right? So you can have that, and you have the CPU ID where the packet was handled with the timestamp. Also, we added the loopback interfaces. So we have that per VRF, and it allows to send and receive packets from Linux into Grout. So it's pretty handy if you want to do inline, for example, routing protocols, or if we would like to implement IPsec, IKey v2 in the future, we could use that mechanism. So for now, it's a bit early to make a demonstration of that, but it's used by the FR plugin, which is under development. Also, we had the L1 cross-connect mode, which I talked about earlier. So it's just a matter of setting the mode to cross-connect, and then you give a peer port, and it will act as a software wire, like TestPMD and IO mode, which is the default mode, I think. All right, so time for demonstration. So let me just switch to my terminal here. So what do I have? So I have a platform where I have a bunch of 25 gig interfaces here. And I have these two ports which have been bound to VFI OPCI. They are ready. We have 1 gig huge pages and CPUs which are isolated. So as you can see, we can use CPUs 10 to 19 and 30 to 39. Right, so what I will start with is I will install Grout first. and then I will start it. So it's just a matter of starting a systemd service like this. So it's started, and so we don't have any 2 meg huge pages, which is fine. First of all, what I will do is that you have a CLI like this, where you can have either interactive shell, or you can use it like a shell, like bash command or whatever, and you have interactive completion like this. So first of all, what I'll do is I will change the affinity of the data path CPUs to 10 and 30. I only need 2 CPUs, which will be fine, like this. And then I will configure interfaces. So it will be ports. So the first port, P0, the args, then also displays all the drivers or PCI IDs that are available like this. And I will create a second port like this. And now show interface. You can see we have P0 and P1, and GR loop 0 was created automatically. We have 1 loopback, which is per VRF. So since we only have 1 VRF at the moment, we only have 1 loop interface. So now I will have a look at the topology we saw in the previous slide. So we have 1 north machine, which is configured with that IP address and a default route through 254. And the south machine is the same thing, but with 200 as in the IP address. So what I'll do is that I will configure, so add IP address 172.16.100.254 on P0, and on P1 I will have 200 like this. As you can see, we have our local interfaces like this, and we don't know anything about these 2 machines here. So since Grout has a real IP stack with all the IPv4 and IPv6 dynamic address resolution, we can directly do ping. We can ping Grout directly, so 172.16.100.254, and Grout will reply, right? So now we can see that Grout has discovered a new next hop, and it has been created 4 seconds ago. And we can also ping the other side, like we want to ping the south machine here, and it will work as well. So what happens in that case is that Grout will receive the packet and then resolve the other side of the wire and then forward the packets. So we can do a quick set trace all. So this will enable packet tracing, as I explained earlier. And now we can ping again, and we can do show trace 1. Oh, wrong packet. Yeah. So in this case, we saw that so the first packet that was dropped here was a LLDP packet sent from the switch, so we don't care. But so this one was forwarded by Grout, and we can see, so there's no ARP resolution here because the next hop was still valid. But if any ARP resolution was required, you would see the ARP packets, request, reply, everything will be present in that side. And then we can also have a look at software statistics, for example. So show stats software. And every node here is a node in the global graph, and so you will see the number of times that node was visited, the number of packets processed in total, and then a bunch of extra stats here. So obviously, cycles per packets here don't mean much because we're not sending traffic at high rates or anything. But you could use that to do hotspot pinpointing, like this node is taking a lot of cycles. Maybe we should have a look at that node process function. Maybe something is off, or I don't know. You can also see the hardware stats, which is using the RT-XStats API. Right. So I think we're good for that demonstration. Let me go back here. So before wrapping up, we had significant contributions from other companies, which is very exciting, because until now we were just 2 people working on the project. Now we are 3 or 4 people, which is nice. So if you are interested, please give Grout a try and give us some feedback. It would mean a lot and it will help. And also, if you have any idea of how you would like to use Grout, what would you do with it, please send us a message either on Slack, via email, or open a ticket on GitHub. That would help a lot. All right. So I think I'm done. So if you have any questions or anything, happy to answer.
Simple question. Are these graph nodes RFC compliant? Do they
Yes.
support all the must and should requirements?
Most of them, yes. So the IPv4 and v6 forwarding stack are following the RFCs. Obviously, it's not 100% complete, so some cases are not supported, but the things that we support are RFC compliant.
Compliant, so that
Yes.
they are production worthy.
Yeah.
And I'm assuming the stats will also go the same way. All the MIB counters will be supported.
So for now, we don't have SNMP compliant MIB counters, but we could provide that at some point if needed. I don't know if that's present in any RFC, by the way, the statistics.
The MIB counters are defined by RFC.
Okay. So maybe we could provide something like that, but maybe that wouldn't be done by Grout itself. That would need to be some kind of external thing that takes Grout stats and converts them to a MIB. I don't know. Sure.
Super. Thanks, Ron. Next up, we've got introducing Argparse by Feng from Huawei. And then it's lunch, so we're almost there.
Hello, everyone. I come from Huawei. I'm from Chengmen. And it's lucky to be the last topic before lunch, because maybe we will discuss it later. My topic is about, sorry for that, it's just atomic. I have to try to another one. Yeah. Sorry. The topic is about introducing agriculture Python library. The agenda is very simple. And the first, I will introduce this new library in DPDK and why we introduce it. And then I will mainly introduce the main features and use also the very simple user examples. And there is also another API I want to introduce. The last is, okay, there is last next, and thank you. This library is upstreamed in DPDK and in last years, and is available in all OS platform. Thanks, Andrew. And also currently is used in 2 examples. So when we introduce this library, and yes, we may see it from other softwares, for example, Python. It has 3 modules to could parenting the argument system get options and Argparse. And for Rust, and there is also mainly CLAT could do the argument parsing. For the mainly used is CLAT command line argument parser. Yes, its goal is to simplify the DPDK argument parenthings. Yes, there are many DPDK argument parenthings in DPDK, yes, in many examples and apps, and also in EL library. The main features, and yes, there's support is just, we could think this, the features is the middle between the get options and Python's agriculture parser library. So it supports the passing option argument, and it could take a no value, required value, and also option value. And it also supports passing opposition argument, and also passing multi-stem argument. For example, the black, the allowed list, and the block list, and many block list, many allowed list. And the next is that it also support atomic generate usage information. It also support issue errors when provided with invalidated argument. And there is 2 ways to parsing the argument. The first way is that just auto cell, and it will used for parsing no value type, for example, int and other other no type. And the second way is the callback. So just we provide a way that you just fill a callback, then you use the callback to parsing the input. Here is one example, and it's in the document of this library. It's very unlike the before and get options, and they spend many different places, and this is just locate one instructions, and yes, and in the main function we just invoke and RT quick passing API, and just in one line. is happy to go introduce another API, and this is the API, and yeah, this library is mainly two APIs. The first, the previous is the many APIs, and the second is that, and is side. I think is side functions of these libraries, and so that people could use this API and to parsing and no values, and yes. For example, the second parameter, the indict, and what I want to interpret the import to the target type. Yes. The next maybe have two plans, and the first is that parsing commas call list, which have many repeat implementation in many examples. The second is that maybe we could use more examples in apps, and maybe currently maybe plan to test DMA perf. Yes. And the new apps maybe are welcome to use these new features. Okay, it's just 5 minutes. 1 second.
Thank you.
Thank you.
Question? Or is everybody super hungry and want to go and get some lunch?
Yes, super hungry.
All right. All right. Thanks for a great morning, everybody. We'll start back up at 2 p.m.
Okay, is it time? I hope everybody got a good lunch. So I'm Thomas Monjalon, working in NVIDIA and for DPDK. Now it's time for a special session that we call Bird of a Feature. I will explain what it is. We have one hour, okay, all together. The idea is that we will choose some topics to discuss. Then we will discuss them in small groups in parallel. And if it is a topic where we need to decide things and there is a conclusion, then we will plan a few minutes at the end of this session to explain the conclusion on stage. Okay? So you will elect one person in each group to present the conclusion, if any. It can also be some free speech, if you without any conclusion. Okay. So the idea is to use this time to progress or to learn more, or whatever you feel is good usage of your time. So I propose some topics. Probably we will choose 2 or 3 topics. Then we can split at each side of the room, and we can also have a group going outside. If it's a small group, we can even go to the sofa here. We have 2 white paper boards, so we can use them. Okay? In general, it's good to explain things. So let's go. So you see the topics I propose. If you have another idea, a request, don't be shy, propose. The topics are, if you want to discuss about RISC API, because there is some work in progress to have a binding on top of DPDK API. If you want to discuss some specific tooling for DPDK, like for debugging, I don't know, anything. We have a lot of people this time with us working on DTS. Big chance, so I encourage you to discuss with them. Maybe you want to learn more. Maybe you want to discuss what is in progress. I know that Paul here has some ideas about some new API, etc. So there are many things to discuss about DTS. So just a reminder, DTS is DPDK Test Suite, main tool for testing. We can also discuss about the release process and planning in general, so it's non-technical. But if you have some concern about how releases are done, or how they are regularly late, or if you want to change the dates, etc., that's a good time to discuss it as well. Or if you just want to complain about me, that's fine. Technical subject, we can discuss cache injection, if you know that. It's a really new cool feature which is under progress for injecting packets directly in CPU cache. Another idea is to discuss about threads in DPDK, because the meaning of L-core in DPDK is maybe too restricted in our APIs. There are many types of threads, and today it's not correctly conveyed in the API, so we can discuss some change here. And last idea is to discuss Flow API in general. We have some Flow API maintainers here, so you can benefit from it to learn more about Flow API, or if you want to discuss the current limitation, if you want to discuss how to better implement it, etc. Topics are free. Any more ideas? No? Yes? Don't be shy. Okay? These are good ideas. So what we'll do is we'll raise our hand for the topics we're interested in, and we'll choose the most popular ones. Okay? So who is interested by Rust? Someone told me Rust is very popular. Okay. Tooling. Anything you want to, new tools you want to add? Okay, 2 people. Testing, DTS. Of course, we'll have a DTS session. Of course. Okay, DTS. Release process. Any complaint? Any change? I wanted to change something. 2 people. Okay, not very popular. Cache injection, technical feature. I think it's worse. Okay, for now we have DTS and cache injection. Thread types, L-core, API design. Okay. Flow API. Okay. Flow API is so perfect, nobody wants to change it. I agree. We just need more implementation in drivers for Flow API. Don't forget it. Okay, so we have 4 candidates actually. I would say DTS, cache injection, L-core. No, only 3. Perfect. So we'll split. Who needs white paper board? I suppose L-core needs a white paper board, maybe? Yes, no, not sure? Yes. And cache injection as well. Are you fine, DTS people, if you don't have a white paper board? We can. You need it? No, if you need it, you can take the L-core one. You need it. Okay. So DTS will be here with a white paper. Cache ingestion will be here with another white paper. And L-core API people will go outside. You can use the coach. Okay? Let's go. We will be back at 2:50 for a conclusion. Thank you, everybody.
Terminology, macros, APIs, the fact that the term L-core doesn't really mean what it used to mean in DPDK, which we need to do some clean up. That's what it's.
Just check that if there are possible. Well, should we start by explaining what DTS is and how it works? How many people know about DTS that are using it? Yeah. Okay. Well, in that case, just to simplify it and just make it visual. Normally, I'll just throw a presentation and I'll explain how DTS works. Usually, you will have 2 devices, one of which is the device under test, and the other is the traffic signal. And this is the machine that runs the DTS itself and orchestrates the test. So that's like the easiest way to visualize it. And the DTS itself is a framework with Python that basically allows you to very hopefully easily write Python tests that use this topology or any other topology you define to run your tests. So you can also run tests on a single machine, single server, and also run we are still developing it, and you we'd like to, so we were hoping that we could get some ideas about what kind of features you think we should add to the framework to provide the facility for you to test the features you can test. Because right now we're concentrating on devices, right? And it's traffic generation.
So it's nice to keep that. It's nice to keep that SPV. So we've got that support. We've also got we want to get API content. We've also got these helper functions that are coming into the SPV class that do some common processes that you might find yourself doing all the time if you're in SPV.
So one of the reasons we wanted to run this as a session is that we want to introduce an API for DTS that will enhance the discoverability of all the features that the framework provides, so that you as a writer of the test, you don't need to know the internals and everything that is inside the framework. So provide one small surface that you want to do all your testing. So to get an idea of what people expect from that and the kind of features that you would like to see or the way you will interact with it.
Give an example of what you do in Rush.
So currently the basic idea is to have a context that will basically mimic this kind of topology, where the context will have a DG and if any functionality that is part of that would appear here as function calls, and we'd like to basically keep them steady and stable across releases of the framework, where we change the internals, but on the surface it will always basically become the stable API, and should be intuitive. Like if you want to send packets from TG, call it TG send packet, or if you want to do something like DT.
So like right now, there's a function called send packets and captures. The process of that is writer. So it's like you grab some packet with VCSR, you call send packets and capture, pass in the packet or the list of packets as an argument, and then that will, so you don't need to know what the internals, that will order SCAPI to send those packets off of the egress interface on the TG, and that will also start up the sniffer here. This is going to send this TG is going to forward it. This sort of comes down to the test suite on the particular topology that you've done, but you'll send it over here, you'll send it back, and the packets get snipped here. So the point is that you don't need to sort of be aware of the framework internals, you just set that. So that's like a very simple example of the kinds of stuff that we're trying to provide so that yes, right, that's the same process.
So I've been hearing that with the legacy DTS, the legacy framework versus the new framework that you do and so can you kind of give us updates and information? How is it different from the legacy version and what
functional. Of course, we want to continue to add in fitting it understanding sort of the API surface. We want to continue to add to the framework such that we're there. The right terms are there, test cases are there, in many cases, a subset of what might be there. And do something about it. So I think there is fairly broad coverage for ETO. So that's why I said to start. I would answer with regards to SVD. So that's basically translating to that. So I can't say if you go look at all of those CTS, you're not going to find any single aspect of ETO that we're still writing some test suite now in the new PTS framework form. But that coverage is becoming pretty comprehensive. The part that isn't is that once you look inside of test suite, which is okay, I guess that's what we do for the core of what's important. Once you look outside of this PhD, we don't really have anything, or we hardly have anything. So for some sort of the other stuff like the crypto testing, that's something that is zero. So that's also, by the way, where it's better if we get some API surface recommendations for that, because test suites are not written. So if we get some recommendations there, that's really helpful. Right, so we don't try and consider like a CBTS to be a North Star. So I mean, there have been a number of test suites that in our meetings we looked at, we assessed. So you said this is either no longer this random feature is no longer supported by DPDK. It's just not a coherent good test suite that makes sense. We're not doing that. So there are a number of test suites that we didn't even want to support the curve. And then of course we want to consider the coverage according to the UPED, not according to some framework from years ago. So as a community lab, yes. So like I said, I mentioned like crypto dev. Like I said, we don't have that in the new framework. So if we want to test that, we have to use the framework. But obviously we don't want to do this forever. So we want to ideally extend the coverage beyond this.
My reading of the code is that DPDS is the framework without the framework, whereas basically every text re-implements everything, all the features that we need. So the DPDS tries to put that in the framework, allowing tests to be much, much shorter. So if you look at the files of all the old tests, there are thousands of lines of code, and the new text is probably 5 lines, because we use the code and put it in the framework. So the framework part is quite mature, as if you judge it by how much functionality does it provide versus the old DPDS. Because it already provides way more than the old DPDS, because the old DPDS provides much more than the framework.
there's no SATA standard, there's no sort of coherent way it's happening, and it's sort of impossible to hardware, but it's sort of impossible to come in and access some like API service, even if deep in the internals someone has made it available in some way, which is almost incomprehensible. So, I mean, that's how you end up in a situation where like legacy DTS is like, it's like almost a million lines of Python, right? So, it's almost impossible to be able to find some code usability. So I'm basically agreeing with you, except that there's so much implemented in so many different ways, and man, it's hard to access that.
We do provide all of this functionality, and we do want to give you only the right tests. So what tests you want to do right now? What kind of features do you want to test?
Yeah, so I mean, yesterday I had a chat with you. What I'd like to know was where we are heading with this framework. It sounds like we are going in the right direction. So assuming we are in the right direction, my question was, it said expand over, it said how easy is to use this. I want to give all the control to the computer rather than proof of people is dedicated to right? It's not only slow, but I don't want it to be just around this This is community project. I want to give it to all of the people who actually day and night using it. So I like to know how it is to actually implement the new test cases, crypto dApp, and even other test cases. Not many people are interested, but like certain contributor or company might be interested in certain test suite, which is not automated. I like them to kind of voluntarily work on and contribute, right? Yeah, that's what That's what I'm trying to do.
And that's one aspect of this is something I was discussing with Patrick as well 2 days ago. Just around how we make it that developers easier use this for regression testing for what's there already. So this is what I was talking about was, you see this diagram here where you got your DTS controller node, traffic generator, or system under test here. Now you can run all of these on one node right now. So I had one of the guys on my team looking at this and gave us all the nice demo when I tried that myself. You can have your DUT with your traffic generator running on a controller node, everything. The only little issue that I have right now is that it requires you to have two NICs, one for running the traffic generator and another one for running test PMD, because most of the tests are doing back stuff. For me, with the different systems that we have, probably could get a system with two NICs, but I'm working on 3-4 NIC drivers, so I'm not going to have two NICs for each of those drivers in my system. So for me, what I think would make this really more useful for a lot of developers is if we get it down to run with one system, but it also only requires one NIC with 2 ports back to back for basic regression. Let's say checking you haven't broken VLAN overflow, checking you haven't broken RSS, all this kind of stuff. You make a change to the driver, you just fire up DTS, do a quick run on your system, and do it. Well, they're two different things. That's yes. if we're looking at testing these types of stuff, or how much you should do it on laptop, it's still all about the idea of making it accessible for the regular developers. Because, yeah, it's one thing having this for regression testing, but we have that for some time, and we're not seeing a lot of DPDK developers writing test cases using DTS, or at least talking about using DTS. Because it's all in the lab. We don't have access to the lab. You know, we could do, but, you know, it's a personal problem the way outside. Either way, I will probably not run CS where hardware, it's not right. I got one because of my speaking slide. I would like, so I think there's a question of what DTS should be positions itself as testing. Are you testing hardware? Are you testing hardware drivers, or are you testing DPDK in general? Because if you're testing hardware drivers, then yes, this completely makes sense, and only person has hardware can actually run the system, and they will have to set up their systems to have the hardware to have a connection to run the actual hardware, make sure that it's not broken. But you're saying something in the library, like a hash library, or I'm fixing some, I don't know, nodes in the Grout library, or whatever, anything else. I don't need hardware. I should be able to just run those tests on my laptop. That's what the unit test framework should be. Because this might be one for the library, so if I'm modifying LPM, I use LPM models for regression testing because it doesn't need hardware. So the evolution of the original DTS is the Intel was already testing the hardware, which is a lot more difficult to do because you can't do a unit test for hardware. And the reason why I think it needs to be in the community is that if other people are trying to develop, trying to fix issues on the drivers for hardware that they have, you know, if they already have the hardware, then they need this framework. It's no good as say the framework for testing the drivers just being on Intel, or the framework for testing the X6 drivers just being with Intel. You know, if people have the hardware, it's nice for them to be able to actually test on it if they were trying out new features themselves. It can also be assigned to check for hardware. So that's where DTS came out of, was for testing drivers. Because after all, the vast majority of open DPDK is drivers. So if you haven't seen that in libraries before, I see that as just go on this library, set calculations, hash library, covered by unit tests, and that's very hard to do. You don't need a whole DTS for that. For testing big hardware, kind of need something like this with the traffic generator. That's my view.
What David mentioned, like this is to me to have the minimum setup. Run on the VM that type. So that was helps the individual.
Yeah, so I was testing moving for IO or manipulation, that type of thing. The answer is but again, we need to get it down to, in order to enable that, we need to get it down to be absolute minimum.
No link topology. Can run the data for the same machine. Yes. So. Yeah, so what I'm saying is, as long as you have a single machine that actually gets the hardware, you can run the machine.
But you need 4 ports of network. So you generally take out cards because the traffic generator will not be for functional tests, whereas the DPDK, so they need to be a different and also requiring 2 gigs for hardware. Is there going to be actual coverage numbers in terms of like so if the vendor, rules it on their link and they see like, okay, this path lead dead is going to take for that many to just or this is the path that I code that's actually
resolve that. So you have to tell them you have to set this up the back.
Yeah, so that's not something that's the code coverage or a test suite. It's not something that's supported right now. It's a great idea to add that. I think reasonably we could do providing the test suite coverage, the test suites first, and then work on the code coverage reports for them. Putting the order right.
You are testing from top down, so you are testing this feature on this. So that's very good. And you let's very good as well.
The thing is, the largest part of that is the drivers. So the driver vendors want to see that they are, like, we want them to see that they are the driver that they're at.
Or the other aspect of it is you also want to see that the likeness features in the same way as things like the RT flow test suite. That's a big one for and again for developers, if you're working on the driver trying to add RT flow support to your driver, being able to quickly go to GTS on it to see before community. And that's what we're going to end up inadvertently hard coding the RT flow behavior through GTS. And Tim's point there, because you not much more than the lab. Yeah, but to run a lab, you're generally submitting your patch. Really, we want people to run DTS before this.
Yeah, so we have made systems available to developers before. If we're going to do so, there has to be a system that is not using CI, start only logging at a time. Or it needs to be scheduled. It shouldn't be a system offline. We've done that before. But we haven't had four systems that we had years or 2 or 3 years ago. We have a storage, we had a number of systems to say, here's 20 systems that are for CI, here's 20 systems that are just a sandbox for people. So I'm very willing to try and make stuff like that available to people. But it would be a limited capacity. It might be enough to certainly be positive. But I think I still believe the first solution is obviously we want it to work in cloud context and it works in cloud context. But the first solution is having it be palatable as possible for people who don't have those resources to make use of the application. So I'm certainly receptive to that suggestion.
DTS is a set of capabilities that's developed. You're saying we go to run DTS locally.
I was trying to agree with the fact that it should be possible for people to write some capacity without expensive hardware. With, say, just one system. Bruce's thing, it's a good goal. One system is helpful. It's something that one developer made recently themselves. So that's a
good as if we could just type one command on our shell or machine.
Solution where you can and use a couple virtual functions of that thing or easy and couple for cartridge.
Slide test virtual function.
Yes, sure.
I mean, it's already, we're a long way there, it's already really cool, really usable, you know, running, okay, it requires 2 NICs. It's not as bad as requiring 2 systems, but you can run it like this. You have one system, 2 NICs, and then it's back to back. DTS, they are the big ones, so it's definitely getting to the point where it's usable for individual developers where they're full of system. So if you can get people started to fly in that scenario, and maybe encourage people to try to get some test cases for existing tests. If I want to fix a bug in our driver for this particular scenario, and maybe motivate me to see as well that yes, test for it, you use it for that, maybe you might have the test case. The more people get using it, the more likely we are to see it. This may be a wall for
So we can let them implement whatever their generator to support the DTS generator. So then we have a framework. They can just add on their plugins part. We can do that.
So that's been raised previously. So right, you're going to have some other application here. Something that doesn't even take communicate from the same what means is even. Yeah. So the first goal is to support the process of the test community. But yes, we have received a suggestion to, in some capacity, support any arbitrary application. I think that starts to, I guess sometimes I should say that it's a good idea. In principle, there's nothing that says we can't do that. The way that this is designed, it does not exist presently. That's something I think we'll have to work with the community towards supporting. Last year, we're learning about Grout business now, so we should provide some support for Grout is on that. So it's a good idea, and a lot of us share that desire. But again, well, yes, I guess to.
So I was going to say, is the cost there, the objective there to make it as easy for third parties to use DTS databases for their own internal test suites. So this is more about providing folks who are not really going to use test reuse the DTS databases. That sounds quite reasonable, rather than saying, rather than have these extra tests for this application to go around itself, make DTS something that's used by users.
Yeah, I agree with that.
Right now it is, but the fact is that we add more based on test people, we added another test code there, test event there. DTS will pretty soon will become pretty generic. We'll hopefully start with more generic loving arbitrary binaries, which may make it more useful, but it's not a tier 1 node for it.
Yeah, exactly.
It may evolve that way.
Because as an application, you're not going to be able to upstream those tests. Upstream the tests, but I'm not against us supporting people testing C++. Obviously, they cannot upstream, so that's not something we want to support.
probably not documented because the person who wrote the API worked for the code that produced X0 and assumed that was how all of these behaved. And suddenly it comes along that, okay, what's the key? It doesn't set the tag. It's like, wow, how weird. So, ideally what the DTS implementation should reveal quite clearly, you'll see you're trying to test and fail one function. Yeah, sure. That also assumes that all the present possible behaviors are already out there. Because take that same situation, you've got 2 or 3 things that all script the tag when they put it in the queue. And we write the test to make that. And then suddenly later on something comes out with a new dig that doesn't do it. And it fails the test. And then we discover one of the problems where we've actually not documented that this is the expected behavior because we haven't thought of any other way of doing it. So anyway. Yeah,
I think we have some takeaways, right? Some good things to work on. So I guess probably that's what we will present.
Processes to get obviously doing things like this is because of something I know you have to maybe don't intend it. But you know, like just maybe
Hey all, we're nearing the top of the hour here, so everybody's going to give a little presentation in just a minute, so we want to start to wrap up. And then we'll do a concluding presentation. Thanks.
Where do you want it? You want it here?
Okay, so we had a quick discussion about the current state and the future of DTS after a brief explanation of what we currently have and our immediate plans. We solicited basically comments and suggestions about where DTS should improve in order to enable everyone to write more tests. And the major features, or major themes of the discussions were about making it easier for developers to run it without having access to the lab, which is why we have a couple of mentions of running tests on a laptop using smaller topologies, so fewer NICs, fewer machines, And we also spoke about being able to do some performance testing, and so that we catch performance regressions. So we should support hardware traffic generators, and we already are in the process of adding support for other generators like T-Rex. But obviously that might not be enough for some, that's why hardware.
Right, I'll just note that I think part of that suggestion was that ensuring that there's an abstraction layer between sort of DTS and between the traffic generator, such that if we implement T-Rex today and it's using that abstraction layer, then Ixia can be implemented for that tomorrow. So just figured I'd throw that in there.
It's like a two-way. And someone asked about adding support for their own DPDK application, which is not upstreamed, and we are definitely open to that. And we will be adding more applications, because currently it's mostly test PMD being used by tests, but we do want to add other applications, other DPDK applications, and also make it easy for people to use it with their own non-upstreamed private DPDK applications, so they can test that even if they don't upstream the test themselves. Did I miss anything?
Oh, and we also received a comment about whether it's possible to provide sort of code coverage reports for the test suite. So the test suite runs, how much of the driver code is actually being touched by that. Sort of right now, we're writing some test suites, and it's testing DPDK, but it's not really telling you how much driver code is being looped in there. So that's sort of something that is not available today, but that's a good suggestion, a good thing for us to provide, and I'm sure that sort of would be helpful to driver developers. So I think that those are the suggestions, but that was really helpful and sort of gives us a bunch of good ideas for things to be providing going forward. So thanks.
So surprisingly, everybody almost were interested in DTS, so the LCore session was abandoned. And we had a small session about cache injection, which was led by what? Oh, it happened? Oh, so you want to talk about it? Do you have something?
Yeah, so I took the initiative to the LCore session because I thought the threading an LCore ID, it was way out of it was not up to date according to how we use it today compared to how it was used like 8 or 10 years ago. I think we reached the conclusion that it's not as bad as I really thought. There's something about mainly there's the worker threads and service calls and management thread and main thread and all that. And what we really should move towards is differentiating between non-preemptible or preemptible threads. So there's a lot of functions that use spin locks that assume the worker threads or service call threads, other threads that might even be a control plane thread. That use features that use spin locks, and because of that they shouldn't have all these different names because it's confusing. We want them just to be described as non-preemptible threads. So that's one thing. We basically just have two types of threads: non-preemptible and preemptible threads. And the documentation for various functions in DPDK should reflect if they're expected to be called from a thread that has an LCore ID or not. And regarding LCore ID, we think a lot of this design pattern where you have an LCore ID indexed array should be used. It's a good design pattern, could be used also for control plane threads. And we should make it easier to do that. And one of the barriers is support for secondary process. And it seemed that it's quite a low barrier to fix that. So secondary processes also support these LCore indexed arrays. And it should be easy to give a management thread or a preemptible thread an LCOR ID. So I think those were the main conclusions from where we want to move with DPDK.
Okay, great. And the last session was about cache injection, led by Watsala, our expert.
Yeah, it was actually a brief discussion. The first thing that we discussed was the technology itself, which was presented in Montreal. But we needed a refresher, so I went through the details. And then the current status is that I have stopped working on the DPDK side of things, and because I was mostly busy with the VFIO part of it. There's this patch in the kernel mailing list. I went over that. Which is to enable this feature in the user space through VFIO. But I got some comments from the maintainer, and it turned out I have to improve it a little more. So there's a V2 that's pending, which I have not sent out. That's the current status of it. So it will be out probably sometime next week. So. Yeah, so the other ask, I think it came from Morton on the mailing list to integrate RTE flow with the steering tags. But my RTE flow knowledge is very limited, so I would rather go ahead and enable the VFIO part, and then someone can help with the RTE flow thing later. Yeah. That was it.
So thank you, Watsala, for working on the kernel side. So I would say that for now we wait for kernel support, and then when it will be there, we will be able to implement it in our DPDK API. And as you said, we could configure cache injection per queue or per flow with RTE flow. That's the goal, but probably next year, because this year is dedicated to kernel side mostly. And anyway, the hardware is either new or coming. So we're on track. Yeah. Okay, good. It was a good session. So now we have a big lunch break. And if you go, lunch break, afternoon break. If you exit the room and you go on your right, you will see a big TV, and in front of the TV there is Oricam, who wants to demonstrate how to use AI to develop some DPDK application. So it looks to be very interesting. Yeah, maybe you don't understand, but just look at it. Thank you.
It is, well, it's
Thank you. baseline had other issues, right? The migration from the ground, whatever. But if you go with architecture 0 and get the latest version, I think we should go back to base of 0 so that the operation can say, let's back off base of 0. Yeah. So, so that is the first step. And then the next step is to look at where else we are spending time. So that's why I added when I found that we are doing explicit release, and I said in the patch. Because if that makes it better, somehow we come down, as we were saying, come below the threshold, the goal is, for a while.
Yeah, that's not really great.
But then we have proof. We have experimentation done something wrong. So we have shown, okay, should now our project as much as we can. And I hope the next time we add 2 videos of as well. So there will be 2. Let's see.
Good work. Look, this, the tobacco is not very busy. So whatever you're running the whole saturated at the moment doesn't backpack. This is like a third of the time. The way I'm framed is to say, like, we think it's better doing these sort of it's like application it's wrong. Can't remove it. These sort of faster. So as we do this with all the insights. So what we can integrate is it could be
exactly, that's what I was thinking. If you have a pulpwood, low saturation.
You have to the threshold migration, and then you have when you start migrating, you can make that Argparse, or you can make the migration easier.
Yeah, I was thinking like per port migration into separate migration. It is more because we are now trying to migrate every 50 microseconds.
No, it's not it's once per second. Yeah, so it's not so long. It's also how many flows you migrate. But in this case, I think but you can always try it. You can change the graph in 10 minutes.
And this 1 millisecond, that is only for throughput migration. For from what I see,
But the data which is
yes, it was 5 one of the tests I just happened is because it's really hard to ask them to get to know
I'm assuming we're all the same for the reasons. Where do you think you never go to the house? Oh, I'm not going to go.
Patrick So we are starting again. Please call people who are still outside. Patrick from the New Hampshire lab, IOL, is going to present his work on DTS.
Great. Testing, testing. All right, hello. So my name is Patrick Robb. I'm coming from the University of New Hampshire Interoperability Lab. And I'm here to give a talk about the DPDK Test Suite, or DTS. We just had a wonderful conversation between a bunch of interested folks about it. And sort of based on that conversation, I'll note at the start that DTS is a end-to-end testing framework for DPDK where basically it sets up multiple nodes and one node will send traffic, the other node will run some DPDK application, test PMD would be some example, then we write some test suites that will set up test PMD, set up the TG, run some workload, do an assertion, and the test will pass or fail. And I'll note that we're running this in a CI lab, but it is not intended to be used exclusively by CI labs. It can be used by individual developers as well. There was a talk at DPDK Montreal last year about how to write test suites and how to run DTS. So I'm sort of building off of that by providing a practical example. And the practical example here is I'm sort of outlining how we set up the framework in our lab automation and sort of what the experience was like for us deploying DTS in basically our automation framework that backs the DPDK community lab. Anyhow, I'll get right into it. So some background information about the interoperability lab and about its relationship with the DPDK project. So the Interop Lab has been hosting a community lab for the DPDK project for some years now. And what we're doing is we basically have some bare metal resources, and we also maintain like a cluster that that basically backs some virtual machines, and we'll run some testing on that. Basically, we run some software testing on the virtual machines, which is like build and unit tests. And the unit tests are being driven by the DPDK Meson test framework. And then on the bare metal side, we'll run some of those end-to-end tests that again, are sending packets from one node, receiving them and processing them with a DPDK application on the other node, and validating that the behavior is correct. And that's the DTS side. That's the thing that's testing the bare metal functions, or the end-to-end testing of a DPDK application. Okay, a couple of other things to note about the community lab is that it's a CI testing lab, so we're doing testing on a per patch basis. So what we do is we monitor the DPDK mailing list for new patches that are coming in from developers. When one arrives, we grab it, we apply it to a particular DPDK tree, and then we run, again, those build tests, those unit tests, and those DTS tests on our hardware. We also will do basically a nightly periodic test on basically all of the relevant DPDK branches. So that's like mainline, the next branches, and then also the LTS branches. So 2211, 2311, 2411. And the final point is that I'll just note that the community lab it exists because it is funded by the DPDK project, and that's coming through the gold members. So one of the benefits of being a gold member is that they're able to send their hardware to the community lab or request that particular hardware be brought into the community lab, and then we do so. We integrate that into one of our test beds, and again, then we'll start running the testing over that hardware. So proceeding on here, I also want to call out a few repos which I might mention during this talk just so that there's no confusion. So the first is the DPDK repo. I'm sure we all know that one. But the important thing to note there is that the DTS framework that I'm talking about is the one that is a subdirectory at the top level of the DPDK repo. There's also a DTS repo which is existing on dpdk.org, and that's the legacy DTS repo. So if this talk inspires you and you want to try and deploy this application and make use of it, just make sure that you're cloning DPDK and you're setting up the application which is in the DTS subdirectory under DPDK. The other repo that will be involved with this talk is the DPDK CI repo, and that's basically a set of scripts which combine to form a CI reference lab. So those are some scripts that can be used for doing all of those tasks that are required to set up a CI lab, like polling patchwork, polling and then pulling the patches, applying those patches to a particular tree, running some of the testing, sending the reports to the test report mailing list. Okay, moving on. I also wanted to just provide a few pictures of the bare metal resources that are at the lab. So we've basically got 2 racks, and the one which is on the left here is the first one we had set up. So that's got some eclectic mix of Intel, AMD, and ARM-based systems that have come in over the years. Some of them are quite old now, and some of them are brand new. So for instance, at the bottom there, we've got like an ARM-based server that we actually got in only a couple months ago. And then on the right side, that's the second rack that we've also been setting up recently, which is all pretty much quite new hardware that came in last year. So again, DTS will get run across these systems, and these systems basically will be paired up against one another. One will be acting as a traffic generator, and one will be acting as a DUT. A DUT or a SUT. Device under test, system under test, same thing. So I'll just overview the topology as it is being set up in the community lab right now. And then at the end, I'm also going to talk about what are the other things, the other ways that you could set up your topology. So basically, you've got 3 entities that we care about. One entity is the traffic generator node. That's what's going to be sending the packets and sniffing them at the end. One entity is going to be the SUT node. That's going to be running some DPDK application. Test PMD is what we're doing in most test cases. And then you've also got the execution host. So that's what's actually running the DTS Python application. And that application or that entity is responsible for controlling the TG node and controlling the SUT node. I'll also point out that you can see there's 2 links that we have here in between the traffic generator and the SUT. That's sort of the standard topology that we're deploying at the lab. Different test suites will have sort of different physical requirements written into them as Python decorators. There are some that do not require 2 links, but rather require 1 link or none. So if you're only able to set up, sort of a smaller topology, you can run a subset of the test suites that exist within DTS, but that's just the one caveat there. And the final thing to clarify is that the TG node and the SUT node, we're setting them up as 2 servers connected back to back, but that's not actually required. If you'd like, you can just have 2 NICs which are both hosted on the same server connected back to back. So it is flexible. All right. So we've got the servers, we've got the NICs, and the desire to test DPDK. Before I talk about how we sort of set up the automation for running DTS in our CI lab, let's just do a quick review on how we go from 0 to running DTS. And it's not a very difficult process, I promise. So to start, you just clone the DPDK repo, or otherwise go to your DPDK source where you've not configured DTS already. You need to set up your SSH user and give that user passwordless sudo on the node or nodes that are making up your testbed. Then you need to fill out the configuration files, which you can find under, again, DPDK/DTS. It's not too onerous. You basically have to set up a nodes YAML configuration file. That's where you provide the server info, the NIC info, huge pages configuration, etc. And similarly, you need to provide a test run YAML config file. And that's going to point out, which node is the traffic generator, which node is the set, do you want to use any VDEVs, what are the build options which you'd like to employ, which test suites to run, stuff like that. Then the next step is that on the DTS execution host, you need to meet the Python dependencies in order to run the application. This is also not very difficult. Basically, we've integrated Poetry with the framework, so you can just use Poetry to install the Python dependencies. For those of you that aren't familiar with Poetry, it's just like a fancy requirements.txt, but just with a few more free features. But that's pretty much a simple process. So that's something that you can probably do in a matter of 10 or 15 minutes, most likely, or less. And from there, you just run Poetry run Python main.py, sit back and wait a few minutes or 10 minutes, however long it takes for the tests to execute. And then when they're finished, DTS will produce on the execution host, it will produce an output directory, and within there you'll find a human readable summary text file, a sort of machine parsable results JSON file, which is more helpful if you're using the application in like an automation context, and then also it will provide some test suite specific log files. So if you're looking for why a particular test suite is failing, then you'd want to look at that particular file. So it's really not super difficult, and in fact, we found when we deployed the application into our CI lab, we were able to do so pretty expeditiously. I'm just providing an example config that we're using on one of the systems. Again, it's not too crazy, so you're going to want to provide some arbitrary name for the node. You're going to want to provide the host name of the system, what the user is that has the passwordless sudo permissions, what's the operating system, what are the ports that are making up that topology, and within there you just provide some basic info. What's the bus address, what's the kernel driver, what's the DPDK driver, and the framework will use that to obviously bind to, say, VFI PCI before we start test BMD, or bind back to the kernel driver at the end. You can set your huge pages configuration, etc. I've kind of cut it off at the end here, but similarly, it provides some basic information about your traffic generator. So, what we did is we set up this config on one of our test systems. It was pretty easy. Here's the other config file I talked about, the test run YAML. Again, basic info that's important for DPDK applications. What are the L cores to use? How many memory channels do you want to employ? We have some configuration for the DPDK source and build options. So do you want to provide a DPDK tarball, or do you just want to provide an uncompressed normal DPDK directory? What are the build options? Actually, I'll call out that Wathsala's talk from earlier made me realize that we really should have like a Mason options or Mason flags key value here, So I made a ticket for that, and we can add that. And then again, some basic information. What is the SCAPI? What is the traffic generator that you want to use? What are the test suites that you want to run? You can either provide a subset or just leave it blank, and it will run the whole set of tests. And again, which system is the traffic generator and which is the site. So it's not a big lift to configure, I promise. This one is going to be less relevant for individual developers that want to run DTS because they do not need to use Docker or containers in order to do so. But for the CI labs, we are providing a Docker file. And the reason is because we don't want to have this problem that containers solve of, it works on my system, why doesn't it work on your system? So we did just write a simple Docker file that will meet all of the dependencies between the sort of Ubuntu, well, you don't have to be using Ubuntu, don't worry, to run DTS, but meet all of the basic dependencies, meet the Python dependencies, and then start the framework. So basically what happens here is that it meets the dependencies, and then we define an entry point. That just means that when the container gets starts, it runs poetry run Python main.py. The framework will execute for a few minutes, and then once the main.py script exits, then the container will exit, and our automation proceeds. So this has sort of made our life easy. And that you can just find that Docker file in the DTS directory. So great. Now we know how we can easily set up DTS. So let's talk about how we sort of integrated that into the CI lab automation. So the way that this sort of plays out as new patches come in is some developer submits a patch to the mailing list. We pull for that. When we see that happening, we use one of those DPDK CI scripts that I was talking about, specifically one called create series artifact. Again, that takes the new patch, or it takes the new patch series, applies it to the correct DPDK tree, and produces a compressed DPDK source that's going to get copied over to the SUT system. And then for each SUT at the lab, we basically set up a set of configuration files. So yeah, for each SUT, we decompress the DPDK tarball, we copy in the configuration files, and we, again, build this DTS runner Docker image and run that. So it's pretty simple. That will run, and that produces the output directory. And we basically have some basic bash that does this, and then it picks up the results JSON at the end. And sort of according to whether the test passed or not, it sends a passing or a failing test report to the test report mailing list. And we also upload the results to the community lab dashboard. So if you see results coming in on Patchwork on your series, sort of that's how that's happening, at least from the community lab perspective. And I did just throw in, again, it's very simple, very short bash that we wrote in basically our Jenkins pipeline. Jenkins, the software that we use to drive the automation pipelines. But with some simple bash, right, we just get our DPDK tarball that has the new patch applied to it, decompress it, CD into it, produce that Docker image I talked about, copy in those two configuration files that we're maintaining on the DTS execution system, and clean up the output directory. And then we run the Docker container. This is all explained in the DTS docs, but I'll just clarify here. The reason we're -v volume mounting in this is that we're copying in our SSH keys so that the DTS execution can control the two nodes and be able to use those passwordless sudo users on the TG and the SUT. And we're volume mounting in the output directory just so that, again, as that output directory gets written to by the DTS execution, and then the container exits, we still have access to those afterwards, because we're going to have to look at those files and then consume them for sending their reports to our dashboard and to Patchwork. Okay. bit of an eye test here. I won't go through every line here, but I just figured I would take some screenshots of what Jenkins is showing. So, some new patch came in. We applied it, we started executing DTS, and then so basically it runs through a test execution setup where it takes control of the two nodes, it gathers some system information, sets up the traffic generator, and then proceeding on, we get into a test suite execution. So it's going to basically take control of the traffic generator on one node, take control of the DPDK application on the other node, and it's going to send some arbitrary, test PMD runtime commands, say. Then it's going to start sending some traffic, and then, of course, we'll have some arbitrary assertion that's in the test suite that defines whether it's a pass or a fail. At which point, we get a result here, and the system cleans up. So again, that was sort of how we set up DTS, how we incorporated it into our community lab pipelines. And then now I'm just going to give a view of how this presents on the dashboard that we maintain. So this is some random patch that came in a week or two ago when I was making this presentation. And I guess it didn't break anything because everything's passing. But as you can see here, we've got a bunch of test suites being run. Some of those are basically the software tests, like the build and the Mason unit tests that I mentioned. I mentioned that we run on VMware, or basically on our VM cluster. And then some of the other tests are either the legacy DTS tests that we're still running on bare metal, or it's the set of new DTS tests that we're running on bare metal in the manner that I've just described. So, digging one level deeper, let's say someone wanted to see the results from DTS for a particular set. And I'm taking the example of an Intel XL710 NIC, which is the one that was configured in the config files I went over earlier. They would scroll down on the dashboard and look at the particular test suites that were run on that set. In this case, everything was passing, so probably someone wouldn't necessarily want to look. But if it was a failing result, a person basically could come here and download the result summaries. That's going to be the stuff that DTS had produced in the output directory, or they can just open it within the browser. So if, say, you clicked Open Artifacts there for the buffer scatter test, you could that would bring you to another page. You could extend that window and see sort of the test suite specific logs for buffer scatter, and sort of learn what you need to learn from the test suite logs. So again, that was sort of the whole process from having nothing to configuring DTS so that it ran, to writing a little bit of bash just so that our Jenkins pipelines could drive it, and it was not a big lift. So some conclusions and considerations looking ahead. So we set up this Jenkins pipeline and started having it drive the DTS framework a couple months ago. It wasn't a big lift, and it's helped us extend our test coverage. So that's been helpful for us. And the other final thing that I want to clarify is that because the new DTS framework exists within the DPDK repository, that presents one opportunity, which is that if you are writing, say, an ethdev feature, you can submit your patch series that adds that feature or modifies some existing function, whatever it may be, and side by side with that, as, say, a final patch in your patch series, you could update a test case in an existing DTS test suite, or you could even add a new test suite, whatever is required. So one benefit is that you can submit patches that are updating DPDK and patches that are updating the test coverage side by side, and those will come in together and get picked up by the CI labs together. A few more next steps to note. So like I said, we deployed this in the UNH community lab, but I'd like to work with, there is a broader set of CI testing labs that are all picking up patches in the manner that we are and submitting some test results to the public mailing list and up to Patchwork. So I'd like to work with those labs to help them deploy this testing framework on their hardware so that we can help extend their test coverage. We've also got some DTS development that I want to call out, which is ongoing but relevant and important. So as an example, we've got like some patch series that are up on Patchwork and continuing to get development for supporting virtual functions. So right now, everything's running through physical functions, but we want to add the VF test cases as well. And we're also adding some support for performance testing and performance traffic generators. So there's another series on Patchwork that's basically adding a performance TG abstraction layer and a support or an implementation for driving T-Rex so that we can run those tests where we send a high amount of packets and we validate that performance is still good. We're also still developing test suites. Like Tama called out yesterday that Dean over at UNH is writing an RTE flow test suite. So of course there were a number of RTE flow talks yesterday. Maybe when we submit that we can CC some of those people and maybe get a review. We're always helpful to get, always grateful to get help from the community. And I'm sure that that would be relevant to all of you people who are relying on RTE flow. So yeah, so there is still plenty of development which is in progress and is a part of the 2507 DTS roadmap, so we're going to keep pushing that forward. And then specific to the UNH lab, we're obviously going to continue adding more network cards and more test beds into the DTS pipelines that, again, I mentioned that we created earlier this spring. So that is a wrap. I wanted to thank some of the people that have been doing a lot of work that has made our usage of this framework possible. So Paul and Luca from ARM have done a lot of work over the past year and have been really instrumental in sort of the framework being as mature and useful as it is. I also want to thank Dean and Nicholas, who are students at UNH, at the UNH Interoperability Lab, and they've been writing a lot of test suites and some framework additions over the past year, so that's been really awesome. And I want to thank Aaron from Red Hat. He's a little bit less on the DTS side, but he's involved with the CI community, and he's been able to help us in a significant way, sort of in terms of the UNH lab operations. I'll point out finally that we do, if you are interested in contributing to this effort, we do hold DTS meetings every other Thursday at 1300 UTC. That's just running through like the Linux Foundation events portal, and I can add you to those calls if you're interested, so please come and talk to me if you're interested in the effort. Thanks again everyone who participated in the DTS Birds of a Feather session. I think we got a lot of really good ideas from that. And a lot of ideas that are going to allow us to put the framework in a really good position for others to be able to come in and make good contributions going forward. So yeah, thanks to everyone for that. And then I'll open it for Q&A. That's all I had.
Quick one, I hope. Is there a list you've got published somewhere of all the test suites that are currently available in DTS and what the requirements are to run them? Because I know there's a config file where you specify what tests you want to run in the test run. Is there a list somewhere of all the possible values for tests that you could specify there so you know what's already done and we can try them out?
Right. Yeah, so there's a test directory within DTS that contains the tests, and each of those tests will have like a doc string that contains the test plan. So I encourage people to go look in there and read the test plans and the test implementations. The way that those will work is that each of the tests basically will perform some capability checks to make sure that they can run on a particular system. This happens at runtime, and it's going through, you know, at DPDK API, it's going through like test PMD, you know, show capabilities. And right, you can also provide some test suite specific config files, and we have like an example config file that in the repository that you can look at. In actuality, most of the test suites don't require particular configuration for the test suite, although that's something that we expect to see more in the future as we start adding in more like performance test suites, because then you're going to have to want to do stuff like set expected baselines that you want to compare against, stuff like that. The test suites also populate up to the DPDK docs when you do a docs build, so it can be read there. But probably the easiest way is to just clone DPDK, you know, CD, DPDK, DTS tests, and then they're all right there. So.
So, good presentation. Thank you. And I have two questions. You mentioned the new framework of DTS, and which is the earliest version of DPDK that includes the new framework?
Right. So I believe that the new framework was added as sort of a experimental work in progress with 2111, but that was an experimental work in progress.
Yeah.
It wasn't really useful for a couple of years. So I don't know about the particular every single .3 and .7 and .11 release, but I would say I can say with confidence if you check out to 2411 that it's a performant testing framework.
Yeah, okay. You suggest the 24.11 to use. Okay.
Yeah, so it's performant on 2411 and also on mainline, of course, so current mainline.
Yeah, okay, thanks. And the second question is, the result, does the result include the coverage rate?
It doesn't include, so right, it doesn't include the code coverage that the test suite reached. That was a subject that got raised in the birds of a feather session, so I guess great minds think alike. There's a couple people that are thinking along those lines. So, I mean, we're taking that down as a feature request, but it's not something that's available right now. Thank you for the idea, though.
Yeah, okay, thank you.
Thanks. Got another one over here. Okay. Any other questions at all for Patrick? No, I think we're good. Thank you. And next we have Aaron Cano from Red Hat, a member of our tech board with patch Smarter, Not Harder.
Okay, anytime? Good? Yeah. Okay. All right. Hi, everyone. I'm Aaron. My agenda is actually pretty short, and I'm here to shame people. Just kidding. I don't know what happened, but... Oh, yeah, okay. Talk over.
Basically, we're doing great.
Yeah, no one to shame. Okay, we'll try it this way. Okay. All right, so DPDK, quite a large community. We get lots of patches, lots of features, there's lots of developers, they all want to integrate something new, right? So the problem is, it's difficult to review all that. It's difficult to, you know, for maintainers to take all those patch files, you know, do the basic sort of sanity checking. Oh, do they do check patch right? Do they, you know, build correctly, run all the testing and all that? These are mechanical processes. Easy enough to automate, easy enough for like, you know, they're just kind of mindless. But they have to get done anyway. So there's a lot of them, right? And so the solution is, let's build a CI, right? Let's build a CI pipeline so that when developers contribute patches, we get some automation that automatically goes through all that sort of, we'll call it mindless work, right? The sort of boring stuff. Meson, Ninja, you know, DTS, for instance. So what happens is we implement a CI pipeline, but it's sort of not stable. People don't trust the results, right? Developers are like, yeah, I don't really care when that thing says a failure. You know, it's not really working right anyway. Hey, the lab is kind of always reporting something broken. The robots have gone haywire. What are we doing? So that becomes the next problem. And the solution is, okay, we work really hard. We make the CI pipeline very stable. I think it's pretty stable now. I think most people would agree. And so the result is developers trust the CI, which is a good thing. But we start to see a weird thing develop, right? The problem is developers stop doing their internal testing. You know, like, hey, okay, I've made a code change. All right, let me check that it builds. As you can see, sometimes it doesn't even compile. So they stop testing, they stop doing even basic sanity checks, right? They stop doing sort of the nuts and bolts of developing a feature and giving it to us. And we end up with, for instance, multiple versions posted in a single day. I just picked this one. You know, or we end up with developers that make so many changes rapidly, again without testing, that they submit 46, 72 patch files. You know, more patch files than even something like maybe NetDev might process in a 2 or 3 week period will come in a single day to DPDK mailing list. But who cares, right? I mean, these are robots running, so it's not tying up anyone's time. Right? So what do? We do some quick little hack. We send it off to the, you know, we decide, it's good enough. I've been coding C for like 30 years, so I'll never make a mistake here. I post it over the fence, right? UNH picks it up. The GitHub robot picks it up. Longson picks it up. Now AWS picks it up. Intel picks it up. Then we see check patch errors. We see compilation failures. We see basic testing issues, right? And so what do you say? Oh, okay, well, I got an email back, right? It's been maybe a half hour. Oh, okay, I'll fix that one thing, right? In my 46 patch series, yeah, throw it off again, right? Who cares? I mean, some robot's gonna test it, so, and then I can go back to drinking Czech beer or watching cat videos, whatever. So every time through the loop, you get a little bit further, but you know, it's still not done yet. And certainly, not high quality, but hey, who cares, right? It's a good thing. In the end, right, by V7, V8, all the lights are green, everything's passing, so it's good now, right? But here's the problem. Every time through that loop, it's not just you tying up 30 minutes on your laptop. You tie up 1,600 minutes of runtime at the IOL. That's a lot of time. That's a lot of compute power. You tie up 190 minutes of runtime at GitHub. I don't know how much time you're tying up at like Intel, Longson, AWS, but it's this, if you add it all up, I mean, you're talking almost 24 hours probably of computers running broken patches, broken test series, broken stuff. Further, each one of those, 46 patch series that has, a missing semicolon or a, bad development piece, each one of those fills up our mailboxes, fills up patchwork, and it makes it actually sort of not enjoyable to actually do a review, because I don't know, when's the next, is there something wrong with this and a robot's going to report it 15 minutes into my review, and then 30 minutes later the next version's going to come and this guy's not going to have addressed any of my comments? I tried to not actually shame anyone, but I'm sure you could figure it out if you really wanted to. But here's an example. This was a build failure, right? And so within an hour and a half, another version posted, which by the way also failed for a build failure. So it's clear this person wasn't actually didn't say, oh, you know what, I rushed this, I should take the time, I should make sure that my next version is really, passing everything and really something ready to review. So like I said, it piles up on the mailing list. It makes reviews feel, maybe a little bit just not really wanting, demotivational. It's a demotivational process. Like, I don't want to review a patch now because, I don't know, is it probably broken, and then some robot's going to come along and tell us all that it's broken, and then I'm going to write some comment that it's broken, and this guy, maybe he's already spun up the next version, and we have to sort of always be chasing that. This gets especially worse during the RC stages. I know like Thomas and David have probably seen it worse than I'm reporting it here, but it gets very bad. There's just like a constant flurry of emails. I think there was one time where Thomas didn't sleep for like a few days in a row. It was, so it's pretty bad sometimes during those cycles. So can we, as developers, do better? And I think the answer is yes. Okay. First thing I will say is, let's say you want to get back to watching your cat videos really quickly, and you really just want someone else to be running this. Well, I mean, at least if you have GitHub, we have support for GitHub Actions already built in. So if you just go to your settings and you allow actions on your GitHub, your private GitHub, you can just push there. It will run all those actions, and you can see, oh, okay, well, I made a build failure. Let me fix this. Let me go ahead and submit the, like the next version to my private. And then once I see everything passing, okay, now at least I know some robot's not going to tell everyone that I didn't bother testing and was busy watching cat videos. I'm showing here something that I started working on. And I'm happy for someone to help. And this is Cirrus CI support, so that we can do like FreeBSD builds. It's currently broken, not because we can't build on FreeBSD. We can compile just fine. But the unit tests don't run. So if anyone wants to help get those running on FreeBSD, I know the lab would appreciate it, because they're only doing compilation on FreeBSD. And yeah, I would appreciate it, because then we could push this in, and then we'll also have a Cirrus robot in addition to a GitHub robot. There are also, I put a link here to like the documentation for running the Meson unit tests. So you can, in fact, just run them on your machine, fast tests and all that, and just get a bit of like confidence that, hey, I made some change and it didn't obviously break anything. So again, it's like sort of an easy thing to do, I think, to just guarantee that, yeah, we're not sort of spending cycles and tying up mailing list and email boxes. And we can sort of relieve the pressure, that comes with just like floods of patches by saying like, if a patch is failing basic compilation, in my opinion, there are bigger issues than just, oh, someone forgot a semicolon. I mean, it's clear that they did not even test. Because if it failed compilation, then how could they have tested? It's not possible. So, multiple versions in a day, you know, so like, at least be testing. Next, like, multiple versions in a day are not useful for getting feedback. This is a global community. There are people spread all over the world, and if we are iterating so quickly on patches, if we're saying like, okay, yeah, here's next version in 5 minutes, next version 10 minutes later, next version 15 minutes later, I don't know, who here, put your hand up if you really want to be reviewing in that environment. Okay, let the record show no one has raised their hand. So I mean, yeah, no one wants to work in that. It's becomes like a write-only thing, you know. Patch series that go so large, well, I have 46 patches, 57 patches, 72 patches. It's difficult to actually review those properly. It's a lot of change going in, a lot of churn going in, and most likely it can be broken down into something smaller, more digestible, and more importantly, then it's not all going in during RC cycle. You can kind of get your stuff in incrementally and work toward, you know, the end date and end goal, slowly, piecemeal at a time, and then it kind of takes the pressure off for everyone. You're not in a time crunch at the end to try and get everything in for the, you know, for the release. The maintainers aren't busy losing sleep trying to merge 115 patch series. You know, that's all good. And then finally, we all need to be mindful of the community resource that we're taking up. When you tie up those 1,600 minutes of time at IOL, no one else can use those. Those systems are being in use for your patch series that maybe it's not ready. So, you know, if you take some time on your local system or using some of the sort of, we'll say, free public stuff available like GitHub Actions even, you can make it so that you're not tying up resources on patches that just aren't going to get merged anyway. So we want to avoid a write-only mailing list, right? If there's 1,000 patches flying by, like LKML, the main mailing list, is a write-only mailing list. No one reads it. Everyone goes to their subsystem mailing list and all that because the number of patches is too high, right? And the number of versions, everything would be too high and all that. DPDK, we don't break it out like that. We have a single mailing list. And if you're submitting a patch every, you know, hour, if everyone does that, it becomes like just a fire hose of emails that's impossible really to review. And if it's like coming every hour, then also you're discouraging people from reviewing it. You're kind of signaling, yeah, I'm not actually testing this. I'm not actually doing, you know, the development work on it. I am using the community resources as a compiler. So, I've kind of codified all this stuff into like a documentation update, and I did send an RFC to the mailing list, and I CC'd everyone in the maintainers file. And thank you, Thomas, for feedback, and I know I brought this up at the tech board. And then finally, I submitted it after addressing comments to as patch, and hopefully it will get merged. And the basic idea is keep your patches small. Don't submit more than one version of your patch within a 24-hour period. You know, unless you're specifically directed to. Like, if you're fixing something super critical and, you know, you spun it up and it failed some test and Thomas emails you and says, you know, publicly on the list, hey, just submit a new version now because as long as it passes, then we'll merge it. Okay, that's one thing. You know, or David says, yeah, please spin this right away, we need it. But otherwise, there's nothing that important that 24 hours is like not a you know, difficult thing to just wait. So, finally, that's it. I think I went over time by just a little bit, but if there are any questions, yeah.
All right, this is off. Do we have any questions for Aaron?
I just thinking like, can we block at the source itself? Like if somebody sends the new version within a day, we can stop there itself, right?
Probably, yeah. What we could do is we could have some robot that shames people. So basically, if you submit the next version.
Not shaming the people. I mean, let's not like. I think it comes to the email server, then from there it goes to the right. So we can block it actually. I think some mailing list does in that way. I think we should do that rather than relying on people.
Yeah, we could put some rate limit in. But the problem is, I don't know if there's a way to do a rate limit on like a version of a patch. You know what I mean? Like, I don't want to rate limit someone if they're going to submit a patch, right? Let's say they submit like a patch that's a series that's 3 patches long. But then they do something very nice for everyone, which is they say, okay, I'm going to have to wait 24 hours anyway. Let me go read through and do a review on something, you know, and actually like reply and all that. I don't want to rate limit those replies. I don't want to really rate limit the comments to, you know.
Only the new patches, I think, not the comments. Yeah, only
exactly.
the patches. Yeah.
I don't know how to do that. If we can do that, that would be interesting to investigate.
Any question from Lucas over here?
Thank you. Just a small comment, what we did basically in Suricata. We first do some sanity build tests in the first stage, and only then run all the test suites. So this can save up basically all those unnecessarily minutes spent on the CI itself. Just to run as a basic check first.
Yeah, I mean, we might, so that's something that we could work in the various labs and say like, okay, if something is failing, we can, you know, sort of stop, you know, the other builds that are, maybe we could stop other builds that are in progress because we can say, yeah, this is probably not going to fly, so just don't bother running. It's a good suggestion. We can look into it.
Yeah, thanks.
Got a question from Thomas?
Yeah, sorry for the very technical question. Please, can you show again one of your first slides? Let's go back. Yeah.
Which one?
After? Yeah, this one. Yeah, here you talk about delicious Czech dark beer, but do you really think Kozel is the best one?
No. No. Well, I do enjoy it. I think it's good. My preference when I'm in Czechia is to go to Ufleku.
Thank you.
And the last talk is from Ori Kam of NVIDIA, leveraging AI and RAG to enhance DPDK application development. We got a little preview of this earlier.
Trying to find my mouse. Second. That. Okay. Hello. Today I want to present how we can leverage AI and
and retrieval argument generation, RAG for short, in DPDK. What is the motivation? I'll just explain about the motivation, what is the problem statement, what is the suggested solution, what is basically RAG. I'll give some examples, how we can integrate it into DPDK. I'll try to answer the question, why now to do it? And I'll show a bit of the challenges that basically we'll be facing. About me, it's less interesting. And let's start with how can we leverage AI in DPDK. AI in DPDK can be leveraged in many ways, from automated code reviews. When I said automated, it's not really automatic that you will approve the patch. That's not the idea. The idea is that it can save the iterations and give the user information that this reviewer probably wants to see this one, is looking for something. We have the CI tools that are basically doing the functional stuff but we want the logical stuff. Did you describe right the patch? Did you explain yourself? So something more humanly, if you can call it. We can have unit integration test generation, code improvement and refactoring. This is mainly if you are working inside an IDE. Best practices detection. We can detect if common practices are being employed. Document generation, that's important. And the one thing that I want to focus today is we can help DPDK application developers, which I think all of those things are valid and good, but in this specific presentation, I'm going to focus on how we can help DPDK application developers. Why I'm focusing on this? Again, when we implement most of the logic, it's true for all use cases. The only thing that is then is different. But from my experience currently, I think that when we're application developer, basically are our customers. And each one of them is building his own applications, router, security, load balancer, whatever. And from his point of view, it's his application, that's what he wants. And he knows he needs to integrate DPDK because he needs to get the best performance, and we supply the best performance. But now the question is, when it's trying to implement it, it's hard for him. It encounters some difficulties. For example, DPDK in basic is complex, and by definition, it's also powerful. It's powerful and complex. So how do you do stuff? The learning curve is steep. There are releases. We are a live community. Each time we introduce new features, sometimes we deprecate features. There are a number of ways to implement anything, especially, for example, RTE flow. Each company has its own way of doing things, best practices. So how can a simple developer know what is the best practices? And in general, the general AI tools available today are not good enough for our test case. They will be good if we give them the right data. We'll talk about it later. So basically, it also results in that the user has a difficult onboarding and a bad user experience, which I'm trying to solve. Sorry. What is the solution? Basically, create our own DPDK AI using RAG. And this AI can be used for discovering feature, explaining about feature, giving design guidelines on how to implement stuff, best practices. It can give version control suggestion, and so on. Okay, a few words on what is retrieval augmented generation, RAG for short. Basically, it's an AI technique that enhances large language models by enabling them to retrieve integrate external up-to-date information when generating responses. In other words, basically, it means that we can take the large language model, the LLM, and add it our own data, up-to-date data, that's important. Basically, this approach fixes the two main issues of LLMs, the cutoff date, which basically each LLM has its own cutoff date, usually a few years before it's really developed in the field. And from this day on, it doesn't learn anything new, it's just training. So if we did anything in the last few releases, it's not going to be shown in the AI, in the LLM. Second of all, it's the focus issues. Basically, when the LLM is trained on the most massive amount of data that it can collect. And as much as we are an open community and we have a lot of projects, it's a small drop in the sea. So the model was not trained much on our data, and that limits his responses and the way he thinks. Basically, by adding our own data, we can, first of all, solve the two issues by giving it up-to-date data that he didn't have, and secondly, focus his answers to our data and leverage the fact that he knows how to read documents, but on our documents. Let's see how it works. Originally, we have the user, which connects directly to the LLM. He asks the user, the LLM, a question, the LLM answers. Then, what happens is, now we're introducing a new entity that is called the retriever. The retriever now gets the query from the user. It searches in its own database for the relevant information, and then it sends the original query with the external information, and sometimes with external instructions on how to respond. Then this retriever gets the answer from the LLM. Now this loop can have a number of iterations to fine-tune the answers, to get even more correct information, and only then the user gets the response, which is correct and up-to-date with all sanity and no hallucination, hopefully. Let's look at a few use cases, API changes. Basically, by the way, for the record, I used OpenAI 4.1 in my testing, but just for the record. So I asked the API, the LLM, to run the command to run application on a specific device, and I got the left side. Basically, as we can see, there are two main issues. First of all, is using -W. We didn't use -W for over 5 years, I think. I looked in the code to find out who changed it. It's like 5 years ago. But I guess that most of the examples on the web are older than 5 years, so you got -W. Second of all, we see that he did put the device as an argument to the application and not to the EL. Again, incorrect. By adding it, the information that I copied from EL args include, simply copied it, pasted this information, I got the right result. Let's look at something a bit more complex. Best practices. I took for this example IPsec. I'm not an expert in IPsec. I took it just for the example for this presentation. The basic logic is you receive a packet, you pre-process it, decrypt it, post-processing, and send it to the wire. Now, a user, application developer can simply write this pipeline, but it will not really leverage the DPDK. So let's see what AI gave me as a result. Simply, it's maybe hard to read, but it just gave me general concept about project organ structure using Mason, how to initialize, how to init. It's true, everything is correct, but it's the basic. It's doesn't give me anything about my own IPsec applications. The only thing that might be relevant is that number 3 that he says, use IPsec library. That's it. And that's the end of it. And by the way, we can see that he recommends to use number of cores in the end there, which is correct. So in this case, I gave him a bit more information. If we have time, I can show you exactly the information, but around 20 lines of text. Basically, and I told him that the best practice is basically to use multi-core, but in this example, I wanted to use not just multi-core. I wanted also to separate between the data, receiving the data and sending them, to the decryption. Since the decryption is slower, I didn't want to slow the system, so I told him that it's better to use that way. I also told him that to use the storing API introduced by Konstantin. Basically, it's a new API. We also heard about it yesterday. It's a great API, and if you look at the documentation, it's quite nice. Inside RT ring, it's described exactly how it works, very pretty. But if you look down, you see a small line that says, it might be used for IPsec. There is no real use case. There is no, why is it good? And how, so user probably, sorry to say, Konstantin, will not find it unless he heard your lecture, and that's a shame. So now I'm saying it's good practice to use the storing. Okay? And of course, if possible, to use offloading. And now we're getting something much nicer, I think. First of all, we're getting a total section that's called application architecture. And it explained to us that how to use the multi-threaded approach. It's introduced the storing API that now people can look at and say, oh, it's interesting, why you recommended this to me. It explains the thread core assignment. It explains the packet flow, what it needs to do in each time. Then it explains that if you have the hardware that allows offloading, offload. Think about if it would be nice if we also give it the offloading supported by each company, then it can really give him if it's true or not. And later on, it's not shown, it shows basically what we saw before. So it's much more user-friendly. It gives the developer much more information to work with. Let's take a look at the last example for today. A test PMD, basically I asked him to create a test PMD that insert a rules that matches source IP and destination IP with counter and send it to Q2 using the template API. He gave me this line as a result. The problem with template API, it's much faster by magnitude than standard API, standard RT flow API, but it requires much more work. So if the user tries to run this line, he will fail. And then he'll try again and understand. And basically, it will take him like 7 tries to make it work, because there is steps that needs to be done before adding this. So by copying the documentation from RT flow, RST, I just copied it. Again, it's important to understand, we have most of the documentation. It's just need to give it to him. Basically, we got the full correct answer, so we see that we need to configure. We need to create a template, the pattern template, the action template, the table, insert the rule, and pull for completion. Basically, as you can see, it's much more complex, and probably if the user just tried it, it will fail, and again, very bad user experience. So how can we add AI to DPDK? First of all, we need the RAG stack. Basically, it includes the LLM, the retriever, some vector DB, and chat UI. If you notice, the first 3 are shared from all use cases that we will want. This is the basic blocks, and it's always true. So those are true for all use cases. The only thing that changes is the chat UI that is more relevant for this specific use case. We need the technology, which is basically open source tools from FISIS, that is vector comparison, iStack and LangChain, which is basically frameworks that basically encapsulate everything I described about getting the response from the user, the request from the user, sending it to the database, sending it to the LLM. So it's an open frameworks that are doing this. The data, we can add the data that we need is basically docs, commit, examples, mailing list, archive, everything that we can think of, and we have already. And the last thing, again, specifically for this feature, the simple chatbot on dpdk.org. Sorry. Why do I think we need to do it now? First of all, our customers are using AI, at least most of them, and if they're not, they will. Either by using open direct access or using AI-powered IDEs, but they are using it, and when they're using it, they're getting bad results. It's even worse than just saying, I don't know, it's leading them the wrong way. So that's super bad user experience. Secondly, we need the RAG tools. The RAG tools are mature, LangChain, iStack, it's a totally open frameworks, free, open sourced, so we don't need to invent the wheel at all. And most importantly, the LLMs are accessible, they're changing, they're evolving, and we just need to use them, to deselect the one that we're using. Nothing is coming without a price. So basically the price here is that we need to create data. For example, best practices we don't have, we need to create it. Sometimes in order to help the AI, we need to format our documentations a bit differently. But we can use the AI to do so, because we can say, this is the feature I did, and how can I write it better so you will understand? The AI will answer us. We need to build the general infrastructure. Either if we're using open source frameworks or not, we need to build it. The most painful thing is the continuous maintenance. First of all, we need to keep the vector DB up to date, and we need to keep leveraging and testing for newer models, how they are affecting our results, and if we need to change the prompts, how new data is changing our results. So we need to continuous working with it. We cannot stop doing it in one shot, and that's it. Fourth, we have the hosting integration. The hosting and integration, basically we need to host it, we need to integrate it in our 2D DPDK site. And we have the cost, of course. LLM costs money, vector database costs money, so there is a money. But usually LLMs, at least, which are the major cost factors, are paid by demand. So if nobody uses them, we will not pay. If somebody is using, we will pay, but that's good. Okay, so that's my final slide. So what I'm proposing. First of all, let's try to create a chatbot for AI, for DPDK. We can use actually now, during my research, we can also use MCPs that even developers that are using AI-powered editors can really ask the questions already from their inside editors and not need to go even to DPDK site. And that's without any extra cost. Of course, how can you help? Basically, I'm here to present and to push forward this idea. So first of all, you can download anything LLM or LM Studio and start to play. You can experience the RAG approach. You can test and support DPDK bot AI GitHub project that I've opened. Again, it's a simple one, but the advantages of the GitHub project is that unlike standard RAG, where we have vector database and we don't know what is inserted, in this case, we have full control on what you insert for the question, so you can learn what helps the AI, what it doesn't like, what it likes better, and then we can move forward. I didn't want to wrap up everything, so it will be black magic. And of course, you can advocate for this in the community and say, okay, we want to, it's not an easy work, and basically, I don't think I can do it alone. I don't have that much free time, unfortunately. And if you have any questions, want to support anything, you can reach me using the mailing list or at my mail. That's it. Thank you.
Do we have any questions for Ori?
No.
Any questions at all? Okay.
Thank you.
Yep. Okay, we got closing remarks now from our lead maintainer, Thomas.
Hello. Okay, wait a minute. Yeah, sorry, I need a chair because it can be long. Yeah, it's not closed yet. This nice summit, this nice 2 days. I hope you enjoyed it. Did you? Yeah? Cool. So, first of all, because we are going to close, I want to thank you, everybody attending, the speakers, the organizations, etc. Thank you, everybody. Of course, I need to remind you how to contribute. You know, I'm doing it every time, every year. It's not a joke, it's really important. That's how the community is living. So I know that every time there is a summit, I meet new persons who want to upstream new drivers or new ideas, etc. That's really great. Thank you for that. But you know what? You can do something else as well. For instance, you can help for testing, and if you see something wrong, you can report it. We have a Bugzilla, please use it. You can also help by reviewing some patches, or just starting a new discussion, bringing new ideas, improving the documentation. All these things are very useful, I can promise. And special mention for mentoring, because sometimes we have some ideas that, oh, maybe we could organize something special, an event or a challenge, etc. But okay, yeah, but who will mentor? So in this kind of cases, we can ask some mentors, and it can happen maybe next month, next year. So that's another way to help. So if you are volunteer to do this kind of things, please volunteer. Yeah, and of course, if you have enough time, you can also become a maintainer. We don't have too much maintainer, too many, don't worry, you are welcome. Okay, talking about contribution, some people are sending some patches. It's another way to contribute. And recently, I mean by recently, since the last summit in Montreal, some people reached the bar of having 10 patches merged in the code base. So you can see all the names. Thank you to all of them. If you are one of them, please raise up and come to me. I have a gift. Watsala, I see you. Paul. Who else? Thank you, guys.
Thank you.
And we have t-shirts. Like L, XL, please help me.
L.
Yeah. Have me only one L. Remaining t-shirt, XL. Thank you. These are our new apprentices. But you know what? We have new magicians. Yeah, they have reached the bar of 50 patches merged. And if you are one of them, Luca, you can raise. Stand up. I think it's XL. Yeah.
Okay.
It's okay for you? Thank you. Yeah, good to have new magician on board. And we also have some... Wow. Okay, my laptop goes to sleep because at the end of the summit he wants to sleep as well. New wizard. 100 patches merged already in DPDK. Are you one of them? Matthias? Darius? Thank you. If the size doesn't fit, we can try to change it.
Sure.
Excel. Excel?
Yeah.
Sure. We'll do that. Thank you. Okay, 100 patches, that's a lot. I think that's all. Oh no, yeah, no, that's all. No sorcerers this time. Maybe you next time. Just need to work a little. But I want to give special mention to some old maintainers who are here around for a long time, and recently they've reached the bar of thousands of patches merged. Can you imagine that? We have David Marchand here with us. You reached the bar, David. Thank you. And this one is the size for your wife. Sure.
How do you know?
Medium fit.
Thank you.
Thank you. Okay. Do we have more? Yeah, all the enchanters coming here. Thank you everybody for being here. It was a great time. Thank you. Now my laptop can sleep, for real. We have more glasses and t-shirts, probably not the right size, but you can check it at the counter.